Before we dive in, I want to hear from you. Drop a comment right now and tell me where you're watching this from, your city, your country, and most importantly, what time is it where you are right now? Are you winding down for the evening? Is it the middle of the night and you can't sleep? Maybe you're halfway across the world, starting your day? There's something oddly comforting about knowing we're all scattered across this one planet, wondering if there's another one out there, just like it. Now, settle in, let the day fade away. Forget about your to-do list. Forget about what time you need to wake up tomorrow. For the next while, time doesn't matter. We're going to talk about something that's been quietly unfolding in the world of astronomy, something that most news outlets mentioned once and then moved on from, but the implications are still rippling through the scientific community. They found it. Earth 2.0, the planet we've been searching for since we first realized that Earth wasn't the center of the universe, and yet, as we'll discover together, this momentous finding reveals truths about our cosmic neighborhood that are far stranger, more complex, and infinitely more humbling than anyone anticipated. The story begins with a moment that should have been pure celebration. On July 23, 2015, NASA held a press conference that captured global attention. Scientists announced the discovery of Kepler 452b, a planet they confidently labeled as Earth's older, bigger cousin. The media exploded with headlines about Earth 2.0, humanity's potential new home among the stars. For a brief, shining moment, it seemed we had found our answer to one of the most profound questions ever asked. Are we alone in having a world that could harbor life as we know it? The initial data seemed almost too good to be true. Here was a planet orbiting a star remarkably similar to our Sun, at nearly the exact same distance that Earth orbits our solar companion. The planet was larger than Earth, certainly, but not so large as to be completely alien. It completed an orbit around its star every 385 days, tantalizingly close to our own 365-day year. Most remarkably, it sat squarely within what astronomers call the habitable zone, that Goldilocks region where liquid water could theoretically exist on a planet's surface. But as with so many discoveries that seem to offer simple answers to complex questions, the reality of Earth 2.0 proved to be far more nuanced, problematic, and ultimately mysterious than those initial headlines suggested. The deeper scientists dug into the data, the more questions emerged. And those questions, when taken together, paint a picture of our galactic neighborhood that is both more wondrous and more lonely than we ever imagined. Kepler 452b sits approximately 1,800 light-years away from Earth in the constellation Cygnus. To put this distance in perspective, our fastest spacecraft, New Horizons, which flew past Pluto and continues its journey into the outer solar system, would require roughly 30 million years to reach this supposedly Earth-like world. Even if we could somehow travel at 10% the speed of light, a velocity that remains far beyond our current technological capabilities, the journey would still take 18,000 years. This is not a world we will visit. It's not even a world our descendants, 1,000 generations from now, are likely to visit. Yet distance was merely the first of many sobering realities that began to emerge as astronomers studied this distant world more carefully. The planet's size, initially seen as encouragingly similar to Earth, soon revealed itself to be more problematic than promising. With a radius about 60% larger than Earth's, Kepler 452b falls into a category that astronomers somewhat optimistically call super-Earths. The reality of super-Earths, however, is far from super for anyone hoping to find a habitable world. Current models suggest that planets much larger than Earth face fundamental challenges that make them potentially hostile to life as we understand it. A world 60% larger than Earth would likely have a mass roughly 5 times greater than our planet's. This enormous mass would create surface gravity nearly twice as strong as what we experience here on Earth. While humans might theoretically adapt to such conditions, the implications extend far beyond the inconvenience of weighing twice as much. That crushing gravity would profoundly alter the planet's atmospheric dynamics, geological processes, and even its ability to retain a stable climate over geological time. The intense gravitational field would compress any atmosphere into a much denser configuration than Earth's, potentially creating crushing surface pressures. Volcanic activity would operate under different rules. with lava flows and gas emissions, behaving in ways that have no parallel on Earth. Perhaps most significantly, the higher gravity would make escape from the planet's surface exponentially more difficult. While this might seem like an abstract concern for a world we'll never visit anyway, it represents a fundamental constraint on any hypothetical civilization that might evolve there. Advanced life forms capable of spaceflight would find themselves trapped by the very world that gave them birth, requiring rocket technologies far beyond anything humans have ever contemplated. But these physical challenges pale in comparison to the astronomical realities that make Kepler 452b's long-term habitability deeply questionable. The planet orbits a star that is significantly older than our Sun, approximately 6 billion years, compared to our Sun's 4.5 billion years. While this age difference might seem modest in cosmic terms, it represents a fundamental shift in the star's behavior that has profound implications for any worlds orbiting it. Stars like our Sun and Kepler 452 follow predictable patterns of evolution, gradually increasing in brightness and energy output as they age. Kepler 452 is currently about 20% brighter than our Sun and radiates 10% more energy toward its planetary companion than Earth receives. This excess energy might seem manageable, perhaps even beneficial, but it represents the beginning of a death spiral for any Earth-like conditions that might exist on the planet's surface. As Kepler 452 continues to age and brighten, the increasing energy bombardment will trigger what scientists call a runaway greenhouse effect. This process, which likely transformed Venus from a potentially habitable world into the hellish furnace we observe today, would gradually boil away any oceans that might exist on Kepler 452b's surface. Water vapor would rise into the atmosphere, where ultraviolet radiation from the aging star would break apart the molecules, allowing hydrogen to escape to space, while oxygen either escaped or combined with surface rocks. Current models suggest that this runaway greenhouse process may have already begun on Kepler 452b, or will commence within the next few hundred million years. Rather than finding a world in its prime, suitable for billions of years of stable evolution, we may have discovered a planet in the early stages of its transformation from potentially habitable world to barren, overheated wasteland. The irony becomes even more pointed when we consider that the very features that made Kepler 452b seem so Earth-like in the initial discovery reports may actually make it less suitable for life, not more. Its position in the habitable zone, so celebrated in those early headlines, places it at the inner edge of that zone where increasing stellar brightness will push it into uninhabitable territory relatively quickly in astronomical terms. Even more troubling are the growing questions about whether Kepler 452b is the kind of world we think it is at all. The planet's size puts it precisely in the range where astronomers are no longer certain whether such worlds are rocky planets with solid surfaces or mini-Neptunes dominated by thick, crushing atmospheres surrounding small rocky cores. The distinction is crucial because a mini-Neptune would be utterly inhospitable to life as we understand it, regardless of its position relative to its star. Recent studies of planets in Kepler 452b's size range suggest that many, perhaps most, are indeed more Neptune-like than Earth-like. These worlds would be shrouded in hydrogen and helium atmospheres, hundreds or thousands of times denser than Earth's, with surface pressures that would instantly crush any Earth-based life form. The solid surface, if one exists at all, would lie beneath an ocean of liquid or supercritical water hundreds of kilometers deep, itself buried under an atmosphere that would be utterly alien and hostile. The uncertainty extends to the very existence of Kepler 452b as a confirmed planet. A 2018 statistical analysis of Kepler data suggested that many supposed planetary discoveries, including Kepler 452b, remained statistically ambiguous. The signal that astronomers interpreted as a planet passing in front of its star could potentially be explained by other phenomena, including instrumental artifacts or variable stellar activity. While Kepler 452b hasn't been definitively ruled out as a false positive, it also hasn't been confirmed by independent observations using different methods, This uncertainty reflects a broader challenge in exoplanet science. The techniques used to discover most known exoplanets provide only indirect evidence of their existence. We infer the presence of planets from tiny dips in starlight or subtle wobbles in stellar motion, but these signals can be remarkably difficult to distinguish from the many other processes that can affect how we observe distant stars. The planets that make headlines as potentially habitable represent the most optimistic interpretations of often ambiguous data. In the decades since Kepler 452b's discovery, follow-up observations have been unable to confirm many of the characteristics that made it seem so promising. We still don't know its actual mass, we can't confirm whether it has an atmosphere, and we have no direct evidence of water or any other molecules on its surface or in its air. This uncertainty extends to virtually all potentially habitable exoplanets discovered to date. The handful of worlds that populate lists of Earth-like planets represent our best guesses based on limited, indirect observations. None has been confirmed to actually possess the characteristics, atmospheric composition, or surface conditions that would make it genuinely habitable for Earth-based life. The challenges become even more daunting when we consider the other supposed Earth twins that have captured public attention in recent years. TOI 715b, discovered in 2023 and heralded as another breakthrough in the search for habitable worlds, exemplifies many of the same problems that plague our understanding of Kepler 452b, while introducing entirely new categories of potential difficulties. TOI 715b orbits a red dwarf star, the most common type of star in our galaxy. Red dwarfs make up roughly 3/4 of all stars, and their small size and dim luminosity make planets around them relatively easy to detect. This abundance has led many astronomers to focus their searches for habitable worlds around red dwarf stars, reasoning that the sheer number of such systems would increase our odds of finding truly Earth-like conditions. Yet red dwarf systems present a host of challenges that make them potentially hostile environments for life as we understand it. The habitable zones around these dim stars are extremely narrow and located very close to the stellar surface. Planets like TOI 715b must orbit their stars much more closely than Earth orbits the Sun to receive enough energy to maintain liquid water on their surfaces. This proximity creates conditions that have no parallel in our solar system. Planets in red dwarf habitable zones experience gravitational forces from their stars that are powerful enough to lock them into synchronous rotation, similar to how our moon always shows the same face to Earth. A tidally locked planet around a red dwarf would have one hemisphere in permanent daylight and the other in eternal night, with a narrow band around the terminator line where temperatures might allow for liquid water. The implications of tidal locking extend far beyond unusual day-night cycles. The hemisphere facing the star would likely become scorchingly hot, while the night side would freeze to temperatures that would make Antarctica seem tropical. Any atmosphere would face intense thermal stresses, with hot gases constantly flowing from the day side toward the night side, creating massive, permanent storm systems unlike anything on Earth. More problematically, tidally locked planets would rotate very slowly, making it difficult or impossible to maintain the kind of strong magnetic field that protects Earth from harmful radiation. Our planet's magnetic field is generated by the rapid rotation of its molten iron core, creating electrical currents that produce the invisible shield deflecting dangerous charged particles from space. A slowly rotating world would likely lack this protection, leaving its atmosphere and any potential life on its surface vulnerable to the hostile space environment. Red dwarf stars compound these problems by being notoriously unstable and violent. Unlike our Sun, which maintains relatively steady energy output, punctuated by occasional solar flares, red dwarfs are prone to massive, frequent outbursts that can double their brightness in a matter of minutes. These stellar flares emit enormous quantities of high-energy radiation and charged particles that would blast any nearby planets. Young red dwarfs are particularly violent, producing flares that can be hundreds or thousands of times more powerful than the largest solar flares ever recorded. Such outbursts would strip away planetary atmospheres over relatively short geological timescales, leaving any worlds in their habitable zones as barren, airless rocks, regardless of their initial conditions. While red dwarfs do eventually calm down as they age, their violent youth lasts for billions of years, longer than complex life has existed on Earth. Any planet that managed to retain its atmosphere through this extended period of stellar tantrums would then face the challenges of maintaining habitable conditions on a tidally locked world orbiting a dim, easily variable star. Even the concept of a habitable zone, fundamental to our search for Earth-like worlds, has proven to be far more complicated and uncertain than early exoplanet hunters assumed. The traditional definition assumes planets with Earth-like atmospheres, similar atmospheric pressures, and familiar greenhouse gas compositions. Change any of these assumptions, and the boundaries of where liquid water can exist shift dramatically. A planet with a much thicker atmosphere might maintain liquid water at distances where a thinner atmosphere would result in a frozen world. Conversely, planets with different atmospheric compositions might experience runaway greenhouse effects at distances where Earth-like conditions would be comfortable. The abundance of carbon dioxide, water vapor, methane, and other greenhouse gases can dramatically alter a planet's surface temperature regardless of its distance from its star. These atmospheric complexities mean that simply identifying planets in the habitable zone tells us relatively little about their actual habitability. A world might orbit at the perfect distance for liquid water, while possessing an atmosphere so dense and hot that its surface conditions resemble those of Venus. Alternatively, a planet outside the traditional habitable zone might maintain comfortable temperatures through atmospheric effects we don't fully understand. The search for truly Earth-like conditions requires far more detailed information about distant worlds than our current observational capabilities can provide. Even the James Webb Space Telescope, humanity's most powerful space-based observatory, can only detect the strongest atmospheric signatures from the largest, most favorable targets. The subtle atmospheric characteristics that determine habitability remain frustratingly beyond our reach for the vast majority of potentially interesting worlds. This observational limitation creates a profound irony in our search for Earth 2.0. The planets that make headlines as potentially habitable are often the ones about which we know the least. The most distant, most Earth-like worlds are precisely those that are hardest to study in detail. We can identify their presence and estimate their basic properties, but the subtle characteristics that determine habitability, atmospheric composition, surface conditions, and the presence or absence of water remain essentially unknowable with current technology. Even our most optimistic projections for future observational capabilities suggest that confirming the habitability of distant Earth-like planets will remain extraordinarily challenging for decades to come. The next generation of extremely large ground-based telescopes might be able to detect atmospheric signatures from a handful of the nearest, most favorable targets, but comprehensive atmospheric characterization of worlds like Kepler 452b or TOI 715b will likely remain beyond our reach for the foreseeable future. This technological limitation forces us to confront uncomfortable questions about the nature of our search for Earth 2.0. Are we looking for worlds that are genuinely similar to Earth, or are we looking for worlds that fit our limited observational capabilities and theoretical models? The distinction matters because it affects both our expectations and our strategies for future exploration. The planets that capture public attention as potentially habitable often do so precisely because they fit our existing models and match our current observational capabilities. But this selection bias may be steering us toward worlds that seem Earth-like in our data, while being fundamentally different in reality. True Earth twins might exist in configurations that our current search strategies would overlook entirely. Consider, for example, that Earth itself might not be detected as obviously habitable by alien astronomers using techniques similar to those we employ. Our planet's atmospheric composition has been dramatically altered by the presence of life, with oxygen levels that would be impossible to maintain without constant biological replenishment. An Earth without life might have atmospheric characteristics that would make it seem less promising as a habitable world, despite being perfectly capable of supporting biology once it emerged. This perspective suggests that our search for Earth 2.0 might be fundamentally flawed in its assumptions about what makes a world habitable. We're looking for planets that resemble the Earth we know today, but the Earth that gave rise to life was very different from our current world. Early Earth had a different atmospheric composition, different surface temperatures, and different chemical cycles than the planet we inhabit now. The irony deepens when we consider that some of the most potentially habitable worlds in our galaxy might be completely unlike Earth in their basic characteristics. Planets around different types of stars, with different atmospheric compositions, different surface pressures, or even different fundamental physical properties might provide ideal conditions for life while appearing completely inhospitable according to our Earth-centric models. Recent theoretical work has suggested that worlds we would classify as decidedly un-Earth-like might actually be more conducive to the emergence and evolution of life than Earth itself. Super-Earths, despite their crushing gravity and alien conditions, might maintain stable climates for longer periods than Earth-sized worlds. Their larger size would provide more surface area for chemical evolution, stronger magnetic fields for protection against radiation, and more robust geological activity to drive the chemical cycles that life depends upon. Planets with thick hydrogen atmospheres, previously dismissed as obviously uninhabitable, might actually provide ideal greenhouse conditions for life operating at lower temperatures and different atmospheric pressures than terrestrial organisms. Such worlds could maintain liquid water at much greater distances from their stars than traditional habitable zone models would suggest, dramatically expanding the number of potentially life-bearing worlds in the galaxy. Even more exotic possibilities have emerged from recent theoretical studies. Worlds covered entirely by deep oceans, with no solid surface exposed to space, might provide stable environments for aquatic life forms over geological timescales far exceeding Earth's expected habitability. Planets with thick, permanently cloudy atmospheres might maintain ideal surface conditions through complex feedback mechanisms that have no parallel on Earth. These alternative habitability scenarios suggest that our search for Earth 2.0 might be looking for the wrong kinds of worlds entirely. Rather than seeking planets that resemble our own, we might be better served by expanding our definitions of habitability to include worlds that operate according to completely different environmental paradigms. Yet even this expanded view of habitability runs up against the fundamental constraints imposed by astronomical realities. The distances involved in interstellar exploration remain so vast that even nearby star systems are effectively unreachable with any technology we can currently imagine. The nearest potentially habitable exoplanet lies more than 4 light-years away, a distance that would require tens of thousands of years to cross using our most advanced propulsion systems. The challenge of interstellar travel goes far beyond simple engineering problems. The energy requirements for accelerating even small payloads to significant fractions of light speed are staggering, requiring power sources and technologies that may be fundamentally impossible to develop. Even if we could somehow overcome these energy barriers, the hazards of interstellar space, including radiation, micrometeorite impacts, and the simple logistics of maintaining complex systems over journeys lasting millennia, present obstacles that may prove insurmountable. These practical limitations mean that discovering potentially habitable worlds, no matter how Earth-like they might prove to be, doesn't provide humanity with realistic alternatives to our home planet. Earth 2.0, even if it exists, and even if it's genuinely habitable, will remain forever beyond our reach using any technology we can envision developing. This realization forces us to confront a fundamental paradox in our search for habitable worlds. The discovery of planets that might harbor life satisfies our intellectual curiosity about our place in the universe, but it doesn't offer practical solutions to any of the challenges facing humanity. We're discovering worlds we can study but never visit, contemplate but never explore, wonder about but never know with certainty. The search for Earth 2.0 has also revealed unexpected complexities in our understanding of planetary formation and evolution. The diversity of worlds discovered by planet-hunting missions has shown that planetary systems develop according to patterns far more varied and unpredictable than early theories suggested. Solar systems like our own, with small rocky planets close to the star and large gas giants farther out, appear to be relatively uncommon configurations. Most planetary systems contain types of worlds that have no equivalent in our solar system. Super-Earths and mini-Neptunes dominate the census of known exoplanets, despite being completely absent from our own cosmic neighborhood. This prevalence of unfamiliar world types suggests that Earth-like conditions might be far rarer than we initially hoped, not because potentially habitable worlds are uncommon, but because Earth itself represents an unusual configuration that seldom repeats elsewhere. The processes that create Earth-like worlds appear to require a series of cosmic coincidences that may be difficult to replicate. Our planet formed at just the right distance from a stable, long-lived star. It has a large moon that stabilizes its axial tilt and drives tidal processes that may have been crucial for the emergence of life. It orbits within a solar system whose architecture protected the inner planets from bombardment by asteroids and comets, while still allowing enough impacts to deliver water and organic compounds. Jupiter's presence in our outer solar system has been particularly important, acting as a cosmic vacuum cleaner that swept up debris that might otherwise have pummeled the inner planets. Without Jupiter's gravitational influence, Earth might have experienced impact rates that would have prevented the development of stable oceans and atmospheres necessary for life. These protective factors, combined with Earth's specific size, composition, and orbital characteristics, created conditions that may be genuinely rare in the galaxy. Finding planets that occupy habitable zones around suitable stars may be relatively straightforward, but finding worlds that possess all the additional characteristics necessary to support life as we understand it may prove extraordinarily challenging. The rarity of truly Earth-like conditions would help explain why our searches have turned up so many worlds that seem promising at first glance, but reveal fundamental problems upon closer examination. We may be discovering the galactic equivalent of fool's gold, planets that shine with the promise of habitability when viewed from afar, but prove to be composed of entirely different material when examined more carefully. This possibility raises profound questions about the prevalence of life in the universe. If Earth-like conditions are genuinely rare, and if life requires the specific combination of factors that our planet provides, then biological activity might be far less common in the galaxy than optimistic estimates have suggested. The silence we've encountered in our searches for extraterrestrial intelligence might reflect not the limitations of our detection methods, but the genuine scarcity of worlds capable of supporting technological civilizations. Alternatively, the apparent rarity of Earth-like worlds might simply reflect the limitations of our current understanding and observational capabilities. Life might thrive under conditions we haven't yet learned to recognize as habitable, on worlds that our current search strategies would overlook as obviously unsuitable. The universe might be filled with biological activity operating according to principles we haven't yet discovered. The question of whether we're alone in the galaxy remains as mysterious today as it was before we began discovering exoplanets around other stars. The thousands of worlds we've found have expanded our awareness of the diversity of planetary systems, but they haven't brought us measurably closer to answering the fundamental question of whether Earth-like life exists elsewhere. In many ways, our growing knowledge of exoplanets has made the question of extraterrestrial life more complex rather than simpler. The early optimism that we would quickly find obviously habitable worlds has given way to a more nuanced understanding of the challenges involved in creating and maintaining conditions suitable for life. Each new discovery reveals additional complications and constraints that make habitability seem more precarious and rare. The story of Kepler 452b and other supposed Earth twins illustrates how our initial enthusiasm for finding Earth 2.0 has been tempered by the realities of planetary science and astronomical observation. The worlds that seemed so promising in early press releases have revealed themselves to be far more alien and problematic than those hopeful headlines suggested. Yet this more sobering perspective doesn't diminish the scientific value of studying potentially habitable exoplanets. Each world we discover, even if it ultimately proves unsuitable for life, teaches us something new about the processes that create and shape planetary environments. The diversity of conditions we're finding around other stars provides crucial data for understanding how planetary systems form and evolve. These discoveries also force us to examine our assumptions about habitability and life itself. By studying worlds that differ from Earth in various ways, we can better understand which characteristics of our planet are truly essential for life and which might be incidental features that could be different elsewhere. This knowledge will prove invaluable as we continue searching for genuinely habitable worlds and as we develop more sophisticated models of how life might emerge and evolve under different conditions. The search for Earth 2.0 has also driven remarkable advances in astronomical instrumentation and observational techniques. The technologies developed for discovering and characterizing exoplanets have applications far beyond the search for habitable worlds, contributing to our understanding of stellar evolution, galactic structure, and fundamental physics. The precision required to detect tiny planetary signals has pushed the boundaries of what's possible in ground-based and space-based astronomy. Future missions will continue building on these technological achievements, developing even more sensitive instruments capable of detecting smaller planets around more distant stars. The next generation of space telescopes will possess the sensitivity to analyze atmospheric compositions of some nearby exoplanets, potentially detecting biosignature gases that would indicate the presence of life. However, these future capabilities will still face the fundamental limitations imposed by distance and the physics of observation. Even the most advanced conceivable telescopes will be able to study only the nearest and most favorable targets in detail. The vast majority of potentially habitable worlds will remain beyond our ability to characterize thoroughly, leaving us with tantalizing hints rather than definitive knowledge about their conditions. This limitation means that the search for Earth 2.0 will likely remain an endeavor driven more by statistical inference and theoretical modeling than by direct observation. We may eventually identify hundreds or thousands of potentially habitable worlds, but we'll probably never know with certainty whether any of them actually harbors life or provides conditions suitable for biological activity. The philosophical implications of this limitation are profound. Humanity appears destined to remain fundamentally uncertain about our place in the cosmic community of life. We may forever wonder whether we're alone in the universe without being able to definitively answer that question. The discovery of potentially habitable worlds provides hope that we're not unique, but it can't provide the certainty that many of us crave. This uncertainty might actually be a more interesting and intellectually stimulating situation than definitive knowledge would be. The possibility that we might not be alone, combined with our inability to know for certain, creates a creative tension that drives continued exploration and theoretical development. The search itself becomes as valuable as any answers we might eventually find. The story of Earth 2.0 also reflects broader patterns in how scientific discovery actually works compared to how it's often portrayed in popular media. Real scientific progress rarely involves sudden breakthroughs that provide clear, unambiguous answers to major questions. Instead, it typically proceeds through a gradual accumulation of knowledge that reveals ever more complex layers of nuance and uncertainty. The initial announcement of Kepler 452b as Earth's cousin represented an oversimplification that was probably necessary to communicate the significance of the discovery to a broad audience. But it also created expectations that subsequent research was bound to complicate. The more we learned about this distant world, the more questions emerged about its actual characteristics and habitability. This pattern repeats throughout the history of exoplanet science. Each major discovery generates excitement and optimistic speculation that is gradually tempered by more detailed analysis and follow-up observations. The The process is frustrating for those hoping for simple answers, but it reflects the genuine difficulty of understanding worlds that we can only study through indirect, limited observations. The complexity revealed by studying supposedly Earth-like exoplanets mirrors the complexity we've discovered in Earth's own history and evolution. Our planet's development into a world capable of supporting complex life required an intricate sequence of chemical, physical, and biological processes that played out over billions of years. The more we learn about this history, the more we appreciate how many factors had to align properly to create the conditions we see today. This growing appreciation for the complexity of planetary evolution suggests that finding truly Earth-like worlds may be even more challenging than we initially realized. It's not enough to find planets of the right size in the right location around the right type of star. Those worlds must also have the right atmospheric composition, the right geological activity, the right chemical cycles, and probably dozens of other characteristics that we're only beginning to understand. The search for Earth 2.0 has evolved from a relatively simple problem of finding planets in habitable zones to a multifaceted challenge requiring expertise in atmospheric science, geology, chemistry, biology, and numerous other disciplines. Each field contributes essential insights into what makes a world habitable, but the integration of all this knowledge into comprehensive models of planetary habitability remains an ongoing project. Despite these challenges and complexities, the search for habitable worlds continues to capture scientific and popular imagination. The possibility that we might not be alone in the universe provides powerful motivation for continued exploration, even in the face of mounting evidence that finding genuinely Earth-like conditions may be extraordinarily difficult. Recent discoveries have begun to shift the focus of habitability research toward alternative scenarios that might be more common or more easily detectable than perfect Earth twins. Scientists are developing increasingly sophisticated models of how life might operate under conditions very different from those on Earth, expanding the range of worlds that might deserve closer scrutiny. This broader perspective on habitability might ultimately prove more fruitful than the narrow focus on Earth-like conditions that has dominated exoplanet research. By considering a wider range of potentially habitable environments, we increase our chances of finding worlds that actually harbor life, even if that life operates according to principles very different from terrestrial biology. The search for Earth 2.0 has also contributed to a deeper appreciation of Earth's own uniqueness and fragility. As we've learned more about the specific conditions required for habitability, we've gained new respect for the remarkable series of circumstances that created and maintained the environment we depend on. This perspective lends additional urgency to efforts to protect and preserve our planet's climate and ecosystems. The knowledge that potentially habitable worlds may be rare and distant makes Earth's biosphere seem more precious and irreplaceable. Rather than providing us with alternatives to our home planet, the search for Earth 2.0 has reinforced the critical importance of maintaining the habitability of the world we already possess. The long journey from the initial excitement over Kepler 452b to our current, more nuanced understanding of exoplanet habitability illustrates both the power and limitations of scientific inquiry. We've made remarkable progress in developing techniques for discovering and studying distant worlds, but we've also learned that the questions we're asking are far more complex than we initially realized. The search continues, driven by the fundamental human desire to understand our place in the universe and to know whether we share the cosmos with other forms of life. Each new discovery adds to our knowledge, even when it complicates our understanding rather than simplifying it. The worlds we're finding may not be the Earth twins we initially hoped for, but they're teaching us profound lessons about planetary science, the nature of habitability, and the remarkable diversity of environments that exist throughout the galaxy. Perhaps the most important insight to emerge from decades of exoplanet research is that the universe is far stranger, more diverse, and more surprising than our Earth-centered perspective initially suggested. The search for Earth 2.0 has revealed a cosmos filled with types of worlds that have no parallel in our solar system, operating according to physical and chemical principles that challenge our assumptions about how planets form and evolve. This diversity suggests that if life exists elsewhere in the galaxy, it might be far more alien and operate under far more exotic conditions than science fiction has typically imagined. The search for Earth 2.0 might ultimately lead us not to worlds that resemble our own, but to forms of biology that expand our understanding of what life itself can be. In the quiet of this evening, as you contemplate the vast reaches of space that separate us from these distant worlds, consider that the search for Earth 2.0 has become something far more profound than a simple hunt for habitable planets. It has evolved into an exploration of the fundamental processes that create and sustain worlds throughout the universe, a meditation on the rarity and preciousness of the conditions that gave rise to life on Earth, and a humbling reminder of how much we still don't understand about our place in the cosmic order. The worlds we've found orbiting other stars may not be the Earth twins we initially hoped to discover, but they've provided something perhaps more valuable, a broader perspective on the nature of planets, the complexity of habitability, and the remarkable uniqueness of our own cosmic home. In searching for Earth 2.0, we've gained a deeper appreciation for Earth 1.0, and that understanding may prove to be the most important discovery of all. The story becomes even more intricate when we examine the broader catalog of worlds that have been hailed as potentially habitable over the past decade. Each discovery follows a remarkably similar pattern: initial excitement based on promising orbital characteristics, followed by growing uncertainty as scientists attempt to determine the actual conditions on these distant worlds. The pattern repeats with such consistency that it reveals fundamental limitations in our approach to identifying habitable planets. Consider Proxima Centauri b, the closest potentially habitable exoplanet to Earth at just 4.2 light-years away. When its discovery was announced in 2016, astronomers celebrated finding a possibly rocky planet in the habitable zone of the nearest star to our solar system. The proximity made it seem like a realistic target for future interstellar missions, and scientific papers immediately began exploring the possibilities for robotic probes that might reach this nearby world within a century or two. Yet Proxima Centauri b orbits one of the most violent and unstable stars in our local neighborhood. Proxima Centauri is a red dwarf that experiences massive flares capable of increasing its brightness by factors of 10 or more within minutes. These outbursts bombard any nearby planets with intense ultraviolet and X-ray radiation, levels that would sterilize the surface of any world and strip away protective atmospheres over relatively short time periods. The planet completes an orbit around its star every 11.2 days, meaning it lies close enough to Proxima Centauri to be tidally locked, with one hemisphere in permanent day and the other in eternal night. Even if it somehow retained an atmosphere despite the stellar bombardment, the temperature differences between day and night sides would create atmospheric dynamics unlike anything on Earth, with massive winds constantly flowing between the superheated day side and the frozen night side. More problematically, recent observations have revealed that Proxima Centauri b likely receives 250 times more X-ray radiation than Earth gets from the Sun. This intense high-energy bombardment would not only strip away any atmosphere, but would also break down water molecules and other compounds essential for life as we understand it. The radiation levels are so extreme that they would likely prevent the formation of any complex organic chemistry, the foundation upon which terrestrial biology depends. The challenges become even more severe when we consider that Proxima Centauri, like all red dwarf stars, was far more active and violent during its youth. For the first several billion years of its life, the star would have produced flares and radiation bursts orders of magnitude more powerful than what we observe today. Any planet in its current habitable zone would have been subjected to this intense bombardment throughout the period when life was emerging and establishing itself on Earth. These realities have transformed Proxima Centauri b from humanity's closest, potentially habitable neighbor into a cautionary tale about the challenges of habitability around red dwarf stars. Despite being the most accessible exoplanet for detailed study and potential future exploration, it may represent one of the most obviously uninhabitable worlds we've discovered. The pattern repeats with depressing consistency across the catalog of supposedly Earth-like worlds. TRAPPIST-1, a system that generated enormous excitement in 2017, contains 7 Earth-sized planets, 3 of which orbit within or near the star's habitable zone. The discovery was hailed as a breakthrough, providing multiple opportunities to study Earth-like worlds within a single system. Yet TRAPPIST-1 is an even more extreme example of red dwarf volatility than Proxima Centauri. The star is cooler and dimmer, meaning its habitable zone is even closer to the stellar surface, and its planets are even more tightly bound by gravitational forces. All 7 worlds are almost certainly tidally locked, and they orbit so closely that they experience gravitational interactions with each other that may destabilize their climates over time. The innermost planets in the TRAPPIST-1 system likely lost any water they might once have possessed billions of years ago, their atmospheres stripped away by intense stellar radiation and stellar winds. The outermost planets may be too cold to support liquid water on their surfaces, leaving only a narrow middle zone where conditions might theoretically be suitable for life. But even these middle planets face challenges that have no parallel on Earth. They orbit their star so closely that they complete full orbits in just days or weeks, experiencing rapid changes in gravitational pull that would generate intense tidal heating. This internal heating might maintain liquid water beneath thick ice shells, similar to the subsurface oceans thought to exist on Jupiter's moon Europa, but it would also drive volcanic activity that could make surface conditions unstable and hostile. The gravitational interactions between the TRAPPIST-1 planets create additional complications. The worlds regularly pass close to each other in their orbits, and these encounters can alter their orbital eccentricities, changing how much energy they receive from their star over time. A planet that starts with ideal conditions for liquid water might find itself locked into an elliptical orbit that alternately freezes and overheats its surface as it swings closer to and farther from its star. Recent atmospheric modeling of the TRAPPIST-1 planets suggests that most, if not all, of them lack the thick atmospheres necessary to transport heat from their day sides to their night sides. Without substantial atmospheres, the day sides of these tidally locked worlds would become scorchingly hot, while their night sides would freeze to temperatures where even carbon dioxide would condense as dry ice. The absence of substantial atmospheres likely results from the same stellar activity that makes red dwarf systems so challenging for habitability. The intense radiation and stellar winds from TRAPPIST-1 during its violent youth would have gradually stripped away any primordial atmospheres the planets might have possessed. Unlike Earth, which orbits far enough from the Sun to retain its atmosphere while receiving protection from our planet's magnetic field, the TRAPPIST-1 worlds had no such defenses against their star's assault. These atmospheric losses represent a fundamental challenge for habitability around red dwarf stars that extends far beyond individual systems. The processes that strip away planetary atmospheres operate according to well-understood physics, and they affect virtually all planets orbiting close enough to red dwarfs to be in their habitable zones. The combination of intense radiation, stellar winds, and weak planetary magnetic fields creates conditions that are systematically hostile to atmospheric retention. The problem becomes even more intractable when we consider the timescales involved. Red dwarfs remain violently active for billions of years, far longer than it took for life to emerge and evolve on Earth. A planet would need to survive this extended period of stellar bombardment while somehow maintaining an atmosphere thick enough to support liquid water on its surface. The physics of atmospheric escape suggests that this combination of requirements may be impossible to meet. Some theoretical studies have suggested that planets might replenish their atmospheres through volcanic outgassing, gradually replacing the gases stripped away by stellar activity. However, the rates of atmospheric loss around active red dwarfs appear to exceed the rates at which volcanic processes could replace the missing gases. The net result would still be atmospheric depletion over time, leaving these worlds as barren, airless rocks regardless of their initial conditions. The challenges extend beyond simple atmospheric retention to encompass the entire concept of stable, long-term habitability. Even if a planet around a red dwarf somehow maintained an atmosphere thick enough to support liquid water, the constantly changing stellar output would create climate instability that might prevent the development of complex ecosystems. Red dwarfs are variable stars by nature, with brightness fluctuations that can last for months or years. These variations would cause corresponding changes in planetary surface temperatures, creating climate instability that would stress any life forms attempting to establish themselves. The unpredictable nature of stellar flares adds another layer of environmental chaos that would make it difficult for biological systems to develop the stable chemical cycles that terrestrial life depends upon. The radiation environment around red dwarfs presents additional challenges that go beyond simple atmospheric stripping. The intense ultraviolet and X-ray radiation from these stars would break down organic molecules at the surface of any planet, preventing the accumulation of the complex carbon compounds that serve as the building blocks of life. Even if life somehow emerged in protected subsurface environments, it would face nearly insurmountable obstacles in transitioning to surface-based ecosystems. These radiation effects would be particularly devastating during the early phases of planetary evolution, when simple organic compounds were first forming the chemical networks that might eventually lead to biological activity. The harsh radiation environment around young red dwarfs would likely prevent this crucial phase of chemical evolution from ever beginning, eliminating the possibility of life before it had any chance to establish itself. The cumulative effect of these multiple challenges suggests that the planets around red dwarfs, despite their abundance and apparent accessibility for study, may be among the least likely places to find life in the galaxy. The initial optimism about red dwarf systems has given way to a more sobering assessment of their prospects for habitability, revealing yet another category of worlds that seemed promising but proved to be hostile to life as we understand it. This pattern of initial optimism, followed by growing skepticism, extends beyond individual planetary systems to encompass our entire approach to identifying potentially habitable worlds. The techniques we use to discover exoplanets are remarkably effective at finding planets of certain sizes in certain orbital configurations, but they provide almost no direct information about the atmospheric conditions, surface temperatures, or chemical compositions that actually determine habitability. The transit method, which has been responsible for most exoplanet discoveries, can tell us a planet's size and orbital period with impressive precision, but it cannot distinguish between a rocky world with a thin atmosphere and a mini Neptune with a crushing hydrogen envelope. Both types of planets would produce identical transit signals, leaving astronomers to infer composition based on statistical models and theoretical assumptions rather than direct observations. Similarly, the radial velocity method can provide information about planetary masses and orbits, but it offers no insights into atmospheric properties or surface conditions. A planet might have the perfect mass and orbit for habitability while possessing atmospheric characteristics that make it completely uninhabitable, and our current detection methods would be unable to distinguish between these scenarios. This observational limitation creates a systematic bias in the catalog of potentially habitable planets. The worlds that make headlines as Earth-like are often those that best fit our limited observational capabilities and theoretical models, not necessarily those that are most likely to actually harbor life. We're finding planets that seem habitable according to our simplified criteria, but we have no way to verify whether they actually possess the complex suite of characteristics that true habitability requires. The bias becomes even more pronounced when we consider the types of planets that our current search strategies are most likely to miss. Worlds with unusual atmospheric compositions, uncommon orbital configurations, or exotic surface conditions might provide ideal environments for life while appearing completely unsuitable according to our Earth-centric models. We might be systematically overlooking the most habitable worlds in the galaxy because they don't match our preconceptions about what habitability looks like. The problem is compounded by the enormous distances involved in exoplanet research. Even the nearest potentially habitable worlds are so far away that detailed atmospheric analysis remains beyond our current technological capabilities. The James Webb Space Telescope, humanity's most powerful space-based observatory, can only study the atmospheres of the largest, most favorable targets, and even then, it can detect only the strongest atmospheric signals. For the vast majority of potentially habitable exoplanets, including most of the worlds that have been celebrated as Earth-like, we have essentially no information about their atmospheric properties. We can estimate their masses, sizes, and orbital characteristics, but the atmospheric composition, surface pressure, temperature distribution, and chemical activity that determine actual habitability remain completely unknown. This knowledge gap means that our assessments of planetary habitability are based largely on theoretical models rather than observational evidence. These models, while sophisticated and based on our best understanding of planetary science, necessarily incorporate assumptions and simplifications that may not apply to worlds that formed and evolved under very different conditions than Earth. The uncertainty extends to some of the most basic questions about exoplanet characteristics. For many supposedly Earth-like worlds, we don't know whether they're rocky planets with solid surfaces or mini-Neptunes dominated by thick gaseous envelopes. We don't know whether they have atmospheres at all, much less whether those atmospheres contain water vapor, carbon dioxide, oxygen, or other gases that might indicate habitability or biological activity. This fundamental uncertainty about basic planetary properties makes claims about habitability essentially meaningless for all but a handful of the nearest, most favorable targets. When astronomers announce the discovery of potentially habitable worlds, they're often describing planets whose actual characteristics remain almost entirely unknown. The habitability assessments are based on idealized scenarios that assume the most favorable possible conditions, but these assumptions may bear little resemblance to reality. The situation becomes even more problematic when we consider the role of confirmation bias in exoplanet research. The scientific community, understandably eager to find potentially habitable worlds, may be unconsciously biased toward interpretations of ambiguous data that support the possibility of habitability. When observational uncertainties could be explained by either habitable or uninhabitable planetary characteristics, there may be a tendency to favor the more optimistic interpretation. This bias appears in the language used to describe exoplanet discoveries, where planets are often described as potentially habitable based on their orbital characteristics alone, with little acknowledgement of the many additional factors that would need to align for actual habitability. The media amplifies this bias, with headlines that confidently declare the discovery of Earth-like worlds based on extremely limited information about their actual properties. The cumulative effect of these biases and limitations is a catalog of potentially habitable exoplanets that may be far less promising than it appears. Many of the worlds celebrated as Earth-like may prove to be completely uninhabitable when more detailed information becomes available. The search for Earth 2.0 may have generated a list of false candidates based on incomplete data and optimistic assumptions. Even our most sophisticated theoretical models of planetary habitability may be missing crucial factors that determine whether worlds can actually support life. The models necessarily focus on the characteristics we understand best and can quantify most easily, but habitability may depend on subtle interactions between atmospheric, geological, and chemical processes that we haven't yet learned to model accurately. The complexity of these interactions becomes apparent when we consider how many factors had to align properly to create habitable conditions on Earth. Our planet's specific size, composition, orbital characteristics, and evolutionary history all contributed to creating the environment we see today. Changing any one of these factors significantly might have resulted in a world that was uninhabitable despite orbiting in the traditional habitable zone around a suitable star. The presence of our unusually large moon, for example, has been crucial for maintaining Earth's climatic stability over geological time. The moon stabilizes our planet's axial tilt, preventing the dramatic climate changes that would result from large variations in the tilt angle. It also drives tidal processes that may have played important roles in the early evolution of life, creating regular cycles of wetting and drying that could have facilitated the formation of complex organic compounds. Very few of the potentially habitable exoplanets we've discovered are known to have large moons, partly because such moons would be extremely difficult to detect using current observational methods, but also because the conditions that create large moon systems may be relatively uncommon. Earth's moon likely formed through a massive collision between the early Earth and a Mars-sized object, an event that was probably quite rare in the history of planetary formation. Similarly, the architecture of our solar system, with large gas giant planets in the outer regions that help protect the inner planets from asteroid and comet impacts, may be an uncommon configuration that was necessary for maintaining stable conditions on Earth over billions of years. Most of the exoplanetary systems we've discovered have architectural configurations very different from our own, often with large planets orbiting very close to their stars in configurations that would be unstable or hostile to the development of terrestrial planets. The chemical composition of the materials from which Earth formed also appears to have been crucial for creating habitable conditions. Our planet formed from materials with just the right abundance of heavy elements to provide the chemical diversity necessary for complex geological processes, while avoiding the extreme compositions that might have led to runaway greenhouse effects or other uninhabitable conditions. The specific mix of radioactive isotopes in Earth's interior has powered the geological activity that drives plate tectonics, magnetic field generation, and the chemical cycles that maintain atmospheric composition over time. Different isotope ratios might have led to either insufficient geological activity, resulting in a geologically dead world like Mars, or excessive activity that could have made surface conditions unstable. Even the timing of Earth's formation appears to have been important for habitability. Our planet formed at a stage in the solar system's evolution when the sun was stable enough to provide consistent energy, but not so old that it had begun the brightening process that will eventually make Earth uninhabitable. The specific chemical composition of the solar nebula from which the planets formed provided the raw materials necessary for creating a world with the right balance of rock, ice, and atmospheric gases. All of these factors, and probably many others we haven't yet identified, had to align properly to create the conditions that allowed life to emerge and thrive on Earth. The probability that all these factors would align again on other worlds may be much smaller than early estimates of habitable planet abundance suggested. Rather than being common, truly Earth-like conditions might be remarkably rare events that occur only under very specific circumstances. This possibility would help explain why our searches for habitable worlds have turned up so many planets that seem promising at first glance, but reveal serious problems upon closer examination. We may be discovering worlds that meet some of the necessary conditions for habitability while failing to satisfy other equally important requirements that we haven't yet learned to recognize or quantify. The search for Earth 2.0 has also revealed unexpected complexities in the relationship between a planet's physical characteristics and its potential for supporting life. Early models of habitability focused primarily on a planet's distance from its star and the resulting surface temperature, but more sophisticated analyses have shown that many other factors can be equally important for determining whether a world can support life. Atmospheric composition plays a crucial role that extends far beyond simple greenhouse warming. The presence of specific gases can determine whether a planet maintains stable surface pressures, protects its surface from harmful radiation, and supports the chemical cycles that life depends upon. A world might orbit at the perfect distance for liquid water while having an atmospheric composition that makes it completely hostile to life. Carbon dioxide provides a clear example of how atmospheric composition can determine habitability in unexpected ways. While CO2 is essential for maintaining warm surface temperatures on planets orbiting far from their stars, too much carbon dioxide can lead to crushing surface pressures and extreme greenhouse effects that make surface conditions uninhabitable. Venus demonstrates how a planet at nearly the right distance from its star can become completely uninhabitable due to atmospheric composition alone. Oxygen presents the opposite challenge for assessing habitability. While oxygen is essential for complex life as we understand it, it's also a highly reactive gas that would quickly disappear from planetary atmospheres unless it was constantly replenished by biological processes. The detection of oxygen in an exoplanet's atmosphere would be strong evidence for the presence of life, but the absence of oxygen doesn't necessarily indicate that a world is uninhabitable for other forms of life. Nitrogen, often overlooked in discussions of planetary atmospheres, may be crucial for habitability in ways we're only beginning to understand. Earth's nitrogen-dominated atmosphere provides a stable, relatively inert background that moderates temperature fluctuations and protects surface chemistry from disruption by reactive gases. Worlds with very different atmospheric compositions might be uninhabitable, even if they have the right temperatures and pressures for liquid water. Water vapor itself plays complex roles in planetary climate systems that can either enhance or destroy habitability depending on the specific conditions involved. While water vapor is a powerful greenhouse gas that can help maintain warm surface temperatures, it can also trigger runaway greenhouse effects that boil away planetary oceans. The feedback mechanisms between surface temperature, atmospheric water vapor, and incoming stellar radiation are so sensitive that small changes in any one factor can drive a planet from habitable to uninhabitable conditions. These atmospheric complexities mean that assessing the habitability of exoplanets requires detailed knowledge of their atmospheric compositions, something that remains beyond our observational capabilities for all but the most favorable targets. Even the most sophisticated ground-based and space-based telescopes can only detect the strongest atmospheric signals from the nearest, largest exoplanets, leaving the atmospheric properties of most potentially habitable worlds completely unknown. The challenge becomes even more daunting when we consider that atmospheric composition can change dramatically over planetary lifetimes. A world that starts with ideal conditions for habitability might evolve toward uninhabitable states due to stellar evolution, geological activity, or atmospheric escape processes. Conversely, a planet that seems uninhabitable based on current conditions might have been habitable in the past or might become habitable in the future as conditions change. Earth itself provides a compelling example of how atmospheric composition evolves over time. Our planet's early atmosphere was very different from what we see today, with much less oxygen and very different concentrations of other gases. The atmospheric composition we depend on today was largely created by biological processes over billions of years of evolutionary development, and it continues to change in response to geological and biological activity. This temporal variability in atmospheric conditions adds another layer of complexity to the search for habitable worlds. Even if we could somehow determine the current atmospheric composition of distant exoplanets, that information might not tell us much about their long-term habitability or their potential for supporting life over the extended periods necessary for complex evolution. The magnetic field question represents yet another crucial factor that remains almost entirely unknown for exoplanets. Earth's magnetic field plays essential roles in maintaining our planet's habitability by deflecting harmful charged particles from space and helping to prevent atmospheric escape. Planets without strong magnetic fields, like Mars, can lose their atmospheres to space over geological timescales, transforming from potentially habitable worlds into cold, dry, airless bodies. Generating a strong magnetic field requires specific internal conditions that may be relatively uncommon among rocky planets. A world needs a liquid, electrically conducting core that rotates at the right rate to drive the dynamo process that creates magnetic fields. The size, composition, and thermal evolution of a planet all affect whether it can maintain these conditions over the billions of years necessary for life to develop. Many of the potentially habitable exoplanets we've discovered may lack the internal structure necessary to generate strong magnetic fields. Super-Earths, despite their apparent advantages in terms of surface area and geological activity, might have internal pressures so extreme that their cores solidify into forms that cannot support magnetic field generation. Tidally locked planets around red dwarfs rotate so slowly that they may be unable to drive the dynamo processes that create protective magnetic fields. Without magnetic field protection, planets orbiting active stars like red dwarfs would be particularly vulnerable to atmospheric stripping and surface bombardment by energetic particles. The combination of intense stellar activity and weak planetary magnetic fields creates conditions that are systematically hostile to atmospheric retention and surface habitability, regardless of a planet's position in its star's habitable zone. The geological activity requirements for long-term habitability add another layer of complexity that we currently have no way to assess for exoplanets. Earth's plate tectonics play crucial roles in regulating our planet's climate by controlling the cycling of carbon between the atmosphere, oceans, and solid Earth. Without active geological processes, a planet might not be able to maintain the chemical balance necessary for stable, long-term habitability. Plate tectonics require specific conditions related to planetary size, internal temperature, surface composition, and the presence of water to lubricate geological processes. Many planets that seem suitable for habitability based on their size and orbital characteristics might lack the internal structure or surface conditions necessary to maintain the geological activity that long-term habitability requires. The role of impact history in shaping planetary habitability represents another factor that we currently have no way to assess for exoplanets. Earth's development was profoundly influenced by the timing and intensity of asteroid and comet impacts throughout its history. Early impacts delivered water and organic compounds that were essential for creating habitable conditions, but excessive bombardment could have prevented the emergence of life entirely. The impact history of a planet depends on the architecture of its entire planetary system, including the gravitational influences of giant planets that can either protect inner worlds from impacts or increase impact rates by disturbing the orbits of asteroids and comets. Most of the potentially habitable exoplanets we've discovered are part of planetary systems with configurations very different from our own, and we have no way to assess how these different architectures might affect impact rates and habitability. The biological feedback mechanisms that help maintain Earth's habitability represent perhaps the most challenging aspect of assessing exoplanet habitability. Life itself plays crucial roles in regulating Earth's atmospheric composition, surface chemistry, and climate stability. Without these biological feedbacks, our planet might not have remained habitable for the billions of years necessary for complex life to evolve. This creates a circular challenge for identifying habitable worlds. We're looking for planets that could support life, but true habitability might require the presence of life itself to maintain stable conditions over geological time. A world that seems ideal for habitability based on physical and chemical criteria might not actually be able to support life unless it already has biological processes operating to regulate its environment. The search for Earth 2.0 has thus evolved from what seemed like a relatively straightforward problem of finding planets in habitable zones to a multifaceted challenge that encompasses almost every aspect of planetary science. Each additional factor we recognize as important for habitability makes the search more complex and the likelihood of finding truly Earth-like conditions more remote. Yet perhaps the most profound limitation in our search for habitable worlds is not scientific or technological, but conceptual. We're searching for planets that resemble Earth because Earth is the only example of a habitable world we know. This approach assumes that the conditions that created and maintain life on our planet represent universal requirements for habitability, but this assumption may be fundamentally flawed. Life might emerge and thrive under conditions that we would classify as obviously uninhabitable based on our Earth-centric perspective. The universe might be filled with forms of biology that operate according to principles we haven't discovered, in environments we haven't learned to recognize as habitable, using chemical processes we haven't imagined possible. The search for Earth 2.0, by focusing on worlds that resemble our own, might be systematically overlooking the most abundant and successful forms of life in the galaxy. We might be like astronomers trying to understand the diversity of stars by looking only for objects that exactly resemble our sun, missing the rich variety of stellar types that actually populate the cosmos. This possibility suggests that the apparent failure to find convincing Earth twins might actually reflect the success of evolution in creating diverse solutions to the challenges of life in different environments. Rather than converging on Earth-like conditions, life throughout the galaxy might have evolved to exploit environmental niches that have no parallel on our world, creating a cosmic diversity of biological systems that our Earth-centric search strategies are fundamentally unsuited to detect. The story of our search for Earth 2.0 thus becomes not just a tale of scientific discovery and technological advancement, but a meditation on the limitations of perspective and the dangers of assuming that our local experience represents universal truth. In searching for worlds like our own, we may have been looking in the wrong direction entirely, missing the vast majority of life in the universe because it doesn't conform to our expectations about what life should look like. Perhaps the most important discovery to emerge from decades of exoplanet research is not the identification of potentially habitable worlds, but the recognition that the universe is far stranger, more diverse, and more surprising than our earthbound perspective initially suggested. The search for Earth 2.0 has revealed a cosmos filled with types of worlds and environments that challenge our assumptions about planetary formation, stellar evolution, and the conditions necessary for life. In this vast and unexpected universe, Earth itself appears not as a typical example of what habitable worlds should look like, but as one unusual solution to the challenges of maintaining stable conditions suitable for life. Our planet's specific combination of characteristics may be far more rare and special than we initially realized, making us not just one example among many of life in the universe, but possibly a genuinely unique experiment in the complex chemistry of living systems. This perspective transforms the search for Earth 2.0 from a hunt for alternative homes for humanity into a broader exploration of the fundamental processes that create and sustain complexity in the universe. Whether or not we ever find true Earth twins, the search itself continues to expand our understanding of planets, stars, and the remarkable web of physical and chemical processes that makes life possible anywhere in the cosmos. The technological challenges involved in studying potentially habitable exoplanets reveal yet another dimension of complexity that often gets overlooked in popular discussions of these discoveries. Even our most advanced space-based telescopes can only detect the presence of exoplanets through indirect methods that provide minimal information about the characteristics that actually determine habitability. The gap between what we can observe and what we need to know to assess habitability remains enormous, and it may persist for decades to come. The James Webb Space Telescope, humanity's most powerful space-based observatory, represents the cutting edge of exoplanet characterization capabilities. Yet even JUST can only study the atmospheres of a handful of the most favorable targets, and even then, it can detect only the strongest atmospheric signals. For a planet like Kepler 452b, located 1,800 light-years away and orbiting a relatively bright star, detailed atmospheric analysis remains completely beyond our current technological reach. The challenge becomes apparent when we consider what would be required to definitively confirm habitability for any of the supposedly Earth-like worlds we've discovered. We would need to detect water vapor in their atmospheres, confirm surface pressures compatible with liquid water, identify temperature distributions consistent with stable climate, and ideally detect biosignature gases that might indicate the presence of life. Each of these measurements pushes our observational capabilities to their absolute limits, and obtaining all of them for a single world would require technological advances far beyond what we currently possess. Even for Proxima Centauri b, the closest potentially habitable exoplanet and thus the most accessible target for detailed study, confirming basic atmospheric properties would require observational capabilities that exceed what any planned telescope missions can provide. The planet's proximity to its bright star makes it nearly impossible to separate its faint thermal emission from the overwhelming glare of Proxima Centauri itself. The angular separation between Proxima Centauri b and its star, as viewed from Earth, is roughly equivalent to trying to distinguish a firefly from a searchlight when both are located in another city. The technical challenges of making such measurements have driven the development of increasingly sophisticated techniques for blocking starlight and enhancing planetary signals, but these methods remain limited to only the most favorable circumstances. Future space-based telescopes, including proposed missions specifically designed for exoplanet characterization, might eventually provide the sensitivity needed to study nearby potentially habitable worlds. However, these missions would still be limited to analyzing a small number of the nearest, most favorable targets. The vast majority of potentially habitable exoplanets, including virtually all of those that have made headlines as Earth-like discoveries, will likely remain beyond detailed characterization for the foreseeable future. This technological limitation creates a profound disconnect between the public perception of exoplanet science and its actual capabilities. When astronomers announce the discovery of potentially habitable worlds, the resulting media coverage often implies that we have detailed knowledge about these planets' conditions and habitability prospects. In reality, we typically know almost nothing about their actual characteristics beyond basic size and orbital parameters. The situation is further complicated by the statistical nature of much exoplanet research. Many of the planets celebrated as potentially habitable exist at the margins of detection, where the observational signals are so weak that confirming their existence requires sophisticated statistical analysis rather than clear, unambiguous measurements. The uncertainties involved in these detections are often larger than the differences between habitable and uninhabitable conditions. For planets detected using the transit method, we might know their size to within 10 or 20%, but this uncertainty is large enough to encompass the difference between a rocky super-Earth and a mini-Neptune with a thick gaseous envelope. Similarly, orbital period measurements might be precise enough to place a planet within the habitable zone, but small uncertainties in stellar properties or atmospheric modeling could shift the actual habitable zone boundaries enough to make the planet too hot or too cold for liquid water. These uncertainties compound when we attempt to model planetary conditions based on limited observational data. The computer simulations used to assess habitability must make assumptions about atmospheric composition, surface pressure, geological activity, magnetic field strength, and dozens of other factors that remain completely unknown for distant exoplanets. Small changes in any of these assumptions can dramatically alter the predicted surface conditions, transforming apparently habitable worlds into obviously uninhabitable ones or vice versa. The modeling challenges become even more severe when we consider the complex feedback mechanisms that govern planetary climate systems. Earth's climate stability depends on intricate interactions between atmospheric composition, ocean circulation, geological activity, and biological processes that are still not fully understood despite decades of intensive study. Attempting to predict the climate stability of alien worlds with completely unknown characteristics pushes theoretical modeling far beyond its validated range of applicability. Recent advances in exoplanet atmospheric modeling have revealed just how sensitive habitability predictions are to small changes in initial conditions and model parameters. Computer simulations of supposedly Earth-like planets show that minor variations in atmospheric composition, surface properties, or orbital characteristics can lead to radically different climate outcomes. Worlds that seem ideally suited for habitability in one model become completely uninhabitable when slightly different assumptions are used. This sensitivity to model assumptions means that our current assessments of exoplanet habitability are far more uncertain than is typically acknowledged in scientific papers or popular media coverage. The confidence intervals around habitability predictions are often so large that they encompass everything from ice-covered frozen worlds to Venus-like greenhouses, making the predictions essentially meaningless for practical purposes. The challenge extends beyond individual planets to encompass our understanding of habitability in general. Each potentially habitable exoplanet we study reveals new complexities and unexpected behaviors that force revisions to our theoretical models. The diversity of planetary characteristics we're discovering suggests that habitability may be far more varied and unpredictable than our Earth-based experience initially suggested. K2-18b, a sub-Neptune exoplanet that gained attention when astronomers detected water vapor in its atmosphere, exemplifies how new discoveries continue to complicate our understanding of habitability. Initial reports suggested that this world might have conditions suitable for life, with water vapor detected in its atmosphere and an orbit that placed it within its star's habitable zone. However, subsequent analysis revealed that K2-18b is likely far too large and massive to be a rocky planet with a solid surface. Instead, it's probably a mini Neptune with a thick hydrogen envelope surrounding a small rocky core, conditions that would make surface habitability impossible, even if liquid water exists somewhere within the planet's structure. The water vapor detection, initially interpreted as evidence of potentially habitable conditions, more likely indicates the presence of water within a thick, crushing atmosphere that would be completely hostile to life as we understand it. The K2-18b example illustrates how easy it is to misinterpret limited observational data in ways that support optimistic conclusions about habitability. The detection of water vapor, a molecule essential for life as we know it, seemed to strengthen the case for habitability, but the planet's actual characteristics make surface habitability extremely unlikely, regardless of its atmospheric water content. Similar interpretational challenges affect virtually all potentially habitable exoplanet discoveries. The limited information we can obtain about distant worlds can usually be explained by multiple scenarios, some of which are consistent with habitability and others of which are not. Without additional data that remains beyond our observational reach, we have no reliable way to distinguish between these possibilities. The problem is exacerbated by the natural human tendency to interpret ambiguous data in ways that support exciting or optimistic conclusions. The discovery of potentially habitable worlds generates significant scientific interest, media attention, and public engagement, creating subtle pressures to interpret uncertain data in ways that support habitability rather than ruling it out. This interpretational bias appears throughout the history of exoplanet science, from early claims about planets in the habitable zones of nearby stars that later proved to be instrumental artifacts, to more recent discoveries that have been reinterpreted as less promising as additional data became available. The pattern suggests that many currently celebrated potentially habitable worlds may prove to be far less Earth-like than initial reports suggested. The challenges of studying exoplanet atmospheres extend beyond simple technical limitations to encompass fundamental physics that may be impossible to overcome with any conceivable technology. The light from distant exoplanets is not only extremely faint compared to their host stars, but it also carries relatively little information about surface conditions due to the complex ways that atmospheric gases absorb and emit radiation at different wavelengths. Detecting biosignature gases in exoplanet atmospheres, often cited as the ultimate goal of exoplanet characterization efforts, faces particularly severe challenges that may make definitive detection impossible for all but the most favorable circumstances. Gases like oxygen, which would provide strong evidence for biological activity, exist in Earth's atmosphere at concentrations that would be extremely difficult to detect in the atmospheres of distant worlds using any realistic observational technique. Moreover, the interpretation of potential biosignature detections is complicated by the existence of non-biological processes that can produce the same gases. Oxygen can be generated through the photodissociation of water vapor by stellar ultraviolet radiation, a process that has nothing to do with life. Distinguishing between biological and non-biological sources of atmospheric gases would require detailed knowledge of planetary atmospheric chemistry that remains beyond our observational capabilities. The seasonal and temporal variations in atmospheric composition that characterize Earth's biosphere would be even more challenging to detect in exoplanet atmospheres. These variations, which might provide the strongest evidence for active biological processes, occur on timescales and with amplitudes that would require decades of continuous monitoring with instruments far more sensitive than any we currently possess. Even if we could somehow overcome all the technical challenges involved in detecting and interpreting atmospheric biosignatures, the results might not provide the clear answers about extraterrestrial life that many researchers hope for. Life on other worlds might operate according to biochemical principles very different from terrestrial biology, producing atmospheric signatures that we wouldn't recognize as indicating biological activity. Alternatively, life might exist primarily in subsurface environments that have minimal impact on atmospheric composition, making biological activity invisible to remote sensing, regardless of how sophisticated our instruments become. Earth itself harbors vast communities of subsurface organisms that contribute relatively little to atmospheric composition compared to surface-based photosynthetic life. The subsurface biosphere question raises fundamental issues about how we define and search for habitability in exoplanet research. Most of our efforts focus on identifying worlds that could support surface-based life with access to stellar energy, but some of the most robust and long-lived biological communities on Earth thrive in deep subsurface environments powered by geochemical energy sources rather than sunlight. These subsurface ecosystems might actually be more common throughout the galaxy than surface-based biospheres, since they would be largely immune to the stellar variability, atmospheric instability, and radiation hazards that threaten surface life on many potentially habitable worlds. A planet might be completely uninhabitable at its surface, while hosting thriving biological communities kilometers below ground, in environments that would be completely invisible to any conceivable remote sensing techniques. The possibility that subsurface life might be more common than surface life has profound implications for the search for habitable worlds. We might be systematically overlooking the most abundant and successful forms of life in the galaxy by focusing exclusively on surface habitability and atmospheric biosignatures. Worlds that seem completely hostile to life based on their surface conditions might actually be teeming with biological activity in hidden subsurface realms. Jupiter's moon, Europa, provides a compelling example of how habitability might exist in environments that bear no resemblance to Earth's surface conditions. Europa's subsurface ocean, heated by tidal forces from Jupiter's gravity, might provide ideal conditions for life, despite existing beneath a thick ice shell on a world that receives minimal energy from the distant sun. Similar conditions might exist on countless exoplanets throughout the galaxy, completely invisible to our current search strategies. The Europa example also illustrates how habitability might depend on factors that have nothing to do with a planet's position in its star's habitable zone. Tidal heating, radioactive decay, and other internal energy sources could maintain liquid water and drive chemical cycles on worlds that orbit far outside the traditional habitable zone, dramatically expanding the number of potentially habitable environments in the galaxy. These alternative energy sources for habitability are particularly relevant for planets in multiple star systems, where complex gravitational interactions could generate tidal heating effects far more intense than anything in our solar system. Many of the potentially habitable exoplanets we've discovered orbit stars that are part of binary or multiple systems, creating gravitational environments that might support exotic forms of habitability based on tidal energy rather than stellar radiation. The realization that habitability might depend on internal energy sources rather than external stellar heating has led to a fundamental expansion in how astronomers think about potentially habitable environments. Rather than focusing exclusively on planets in narrow habitable zones around stars, researchers are beginning to consider a much broader range of worlds that might maintain subsurface habitability through alternative energy sources. This expanded view of habitability suggests that the number of potentially life-bearing worlds in the galaxy might be far larger than traditional models suggested, but it also makes the search for such worlds far more challenging. Subsurface habitability would be essentially impossible to detect remotely, and the diversity of possible internal energy sources and chemical environments would make it difficult to predict which worlds might harbor hidden biospheres. The implications extend beyond simply expanding the number of potentially habitable worlds to encompass fundamental questions about the nature of life itself. If subsurface life proves to be more common than surface life, it would suggest that biology might be far more adaptable and resourceful than our Earth-based experience indicates. Life might routinely exploit energy sources and environmental niches that we haven't yet learned to recognize as habitable. This possibility raises intriguing questions about whether our search for Earth 2.0 has been fundamentally misguided from the beginning. Rather than looking for worlds that resemble Earth's surface environment, we might be better served by developing techniques for identifying worlds with active internal dynamics that could support subsurface habitability regardless of their surface conditions. The search strategy implications are profound, since subsurface habitability would require completely different observational approaches than those currently used in exoplanet research. Instead of focusing on atmospheric composition and surface temperature, we would need to develop methods for detecting geological activity, internal heat sources, and subsurface chemical processes from interstellar distances. Some of these alternative detection strategies are beginning to emerge from advances in planetary science and astronomical observation techniques. Measurements of planetary thermal emission might provide information about internal heat sources, while detailed studies of atmospheric composition could reveal gases produced by subsurface geological processes rather than surface biological activity. However, these alternative approaches remain largely theoretical and would require technological capabilities far beyond what any currently planned missions can provide. The signals associated with subsurface habitability would be even fainter and more difficult to detect than the atmospheric biosignatures that already push our observational capabilities to their limits. The time dimension adds another layer of complexity to the search for habitable worlds that often gets overlooked in discussions of specific exoplanet discoveries. Habitability is not a static property that a world either possesses or lacks, but a dynamic characteristic that changes over time as stars evolve, planetary atmospheres evolve, and geological processes modify surface conditions. Earth's own history demonstrates how dramatically habitability can change over planetary lifetimes. Our planet has experienced periods when it was likely completely frozen over, times when atmospheric oxygen levels were too low to support complex life, and eras when greenhouse effects made surface conditions far hotter than today. The Earth we see today represents just one snapshot in a long evolutionary sequence that has included many phases when the planet would not have been considered habitable according to current definitions. This temporal variability in habitability means that assessing whether a distant exoplanet could support life requires not just understanding its current conditions, but predicting how those conditions will change over the billions of years necessary for life to emerge and evolve. A world that seems perfectly habitable today might be on the verge of losing its atmosphere to stellar winds, while a planet that appears uninhabitable now might be entering a phase of its evolution where conditions become ideal for life. The stellar evolution component of this temporal challenge is particularly important for planets orbiting stars very different from our Sun. Red dwarf stars, which host many of the potentially habitable worlds we've discovered, follow evolutionary paths that are completely unlike the Sun's development. They remain violently active for billions of years before settling into stable configurations, creating extended periods when any planets in their habitable zones would be subjected to intense radiation and stellar winds. The question of whether planets can survive these extended periods of stellar hostility while maintaining conditions suitable for life remains largely unanswered. Computer models suggest that atmospheric retention becomes increasingly difficult as stellar activity levels increase, but the models necessarily incorporate numerous assumptions about planetary characteristics that remain unknown for distant exoplanets. Even if a planet could somehow survive the violent youth of its red dwarf star, it would then face the challenge of maintaining habitability as the star gradually settles into a more stable configuration. The changing radiation environment would drive corresponding changes in planetary atmospheric chemistry and surface conditions, potentially requiring complex feedback mechanisms to maintain stable habitability over time. The feedback mechanisms that maintain Earth's long-term climate stability provide examples of the complex processes that might be necessary for sustained habitability around any type of star. Our planet's carbonate-silicate cycle regulates atmospheric carbon dioxide levels over geological time, preventing both runaway greenhouse effects and complete glaciation. The biological components of this cycle, particularly the role of life in accelerating chemical weathering and carbonate deposition, may be essential for maintaining stable conditions over billions of years. Similar feedback mechanisms might be necessary for maintaining habitability on exoplanets, but their operation would depend on specific combinations of geological, atmospheric, and potentially biological processes that we have no way of predicting for distant worlds. A planet might have ideal initial conditions for habitability, but lack the internal dynamics necessary to maintain those conditions over the extended periods required for complex evolution. The geological evolution of potentially habitable exoplanets represents another temporal factor that could dramatically affect long-term habitability prospects. Earth's plate tectonics play crucial roles in regulating surface conditions through volcanic outgassing, chemical weathering, and the cycling of materials between surface and interior reservoirs. Planets with different sizes, compositions, or thermal evolution patterns might experience very different geological histories that could either enhance or destroy their habitability over time. Super-Earths, which include many of the most celebrated, potentially habitable exoplanets, might experience geological evolution patterns that make long-term surface habitability unlikely. The high internal pressures in these massive worlds could prevent the development of plate tectonics, leading to geological stagnation that would gradually reduce atmospheric diversity and surface temperature regulation capabilities. Alternatively, super-Earths might experience such intense geological activity that their surfaces remain unstable and hostile to the development of complex ecosystems. The higher internal temperatures and pressures in these worlds could drive volcanic activity far more intense than anything on Earth, creating atmospheric and surface conditions that would be constantly changing in ways that would stress any biological systems attempting to establish themselves. The internal thermal evolution of planets also affects their ability to maintain the magnetic fields that protect surface environments from stellar radiation. Earth's magnetic field is powered by convective motions in the planet's liquid iron core, a process that depends on maintaining the right thermal conditions in the deep interior over billions of years. Planets with different sizes or compositions might lose their magnetic fields much earlier in their evolution, leaving their surfaces exposed to hostile space environments. Mars provides a compelling example of how magnetic field evolution can affect planetary habitability. Early in its history, Mars likely had a strong magnetic field that protected a thicker atmosphere and enabled surface liquid water. The gradual cooling and solidification of the Martian core shut down the magnetic dynamo, leading to atmospheric loss and the transformation of Mars from a potentially habitable world to the cold, dry planet we see today. Similar magnetic field evolution might affect many of the potentially habitable exoplanets we've discovered, particularly those orbiting active stars, where magnetic protection would be essential for atmospheric retention. The timescales for core cooling and magnetic field decay depend on planetary size and composition in ways that remain poorly understood, making it impossible to predict which worlds might maintain protective magnetic fields long enough for life to develop. The rotation rate evolution of planets adds yet another temporal factor that could affect long-term habitability. Earth's rotation rate has been gradually slowing throughout its history due to tidal interactions with the Moon, but our planet has maintained rotation rates fast enough to support strong magnetic field generation and atmospheric circulation patterns compatible with stable climate. Planets orbiting closer to their stars, including most of those in the habitable zones of red dwarf systems, experience stronger tidal forces that would slow their rotation rates much more rapidly. Many of these worlds might become tidally locked within relatively short periods after their formation, leading to the atmospheric and climate instabilities associated with synchronous rotation. The tidal evolution timescales depend on planetary and orbital characteristics in complex ways that remain difficult to predict accurately. Some planets that initially seem likely to avoid tidal locking might actually become synchronized with their orbital periods relatively quickly, while others that appear destined for tidal locking might maintain rapid rotation for extended periods due to specific combinations of orbital and atmospheric properties. The atmospheric evolution component of temporal habitability changes may be the most complex and least predictable factor affecting the long-term prospects for life on exoplanets. Earth's atmospheric composition has changed dramatically throughout its history, driven by geological outgassing, biological activity, atmospheric escape processes, and changing stellar radiation levels. The early Earth's atmosphere contained virtually no oxygen and had very different concentrations of other gases compared to today's atmosphere. The gradual oxygenation of Earth's atmosphere, driven primarily by photosynthetic organisms, fundamentally transformed our planet's surface chemistry and created the conditions that support complex life today. Similar atmospheric evolution might be necessary for habitability on other worlds, but the specific pathways that atmospheric development follows would depend on countless factors that remain unknown for distant exoplanets. A world might start with atmospheric conditions that seem ideal for habitability, but evolve toward uninhabitable states due to geological or stellar influences, or vice versa. The role of biological processes in atmospheric evolution creates additional complexity that may be impossible to predict without detailed knowledge of potential alien biochemistry. Life on Earth has profoundly influenced atmospheric composition through photosynthesis, respiration, and numerous other metabolic processes, but life on other worlds might operate according to very different biochemical principles with correspondingly different atmospheric impacts. The search for Earth 2.0 has thus revealed that habitability is not a simple binary property that planets either possess or lack, but a complex, dynamic characteristic that emerges from the interaction of countless factors operating over billions of years of planetary evolution. The initial optimism about finding Earth-like worlds has given way to a more nuanced appreciation of the extraordinary complexity involved in creating and maintaining conditions suitable for life. This growing complexity has profound implications for our expectations about finding life elsewhere in the universe. Rather than being a common outcome of planetary formation, true habitability might require such specific combinations of initial conditions and evolutionary pathways that it occurs only rarely, even in a galaxy containing hundreds of billions of stars and potentially trillions of planets. The possibility that habitability might be genuinely rare would help explain the apparent silence of the universe in response to our searches for extraterrestrial intelligence. If most planets that seem potentially habitable based on simple criteria like size and orbital distance actually face insurmountable obstacles to supporting life, then the number of worlds that actually harbor biological activity might be far smaller than optimistic estimates have suggested. This perspective transforms the discovery of potentially habitable exoplanets from evidence that life might be common throughout the galaxy into illustrations of how many ways planetary evolution can fail to produce truly habitable conditions. Each new potentially habitable world we study reveals additional complexities and constraints that make successful habitability seem more precarious and unlikely. Yet this more sobering view of habitability doesn't diminish the scientific value of studying potentially habitable exoplanets. Each world we discover, regardless of its ultimate habitability prospects, provides crucial information about planetary formation, stellar evolution, and the physical processes that shape planetary environments throughout the galaxy. The diversity of exoplanets we're discovering also continues to challenge our assumptions about what constitutes habitability, forcing us to expand our theoretical models and consider alternative forms of life that might thrive under conditions very different from those on Earth. Even if most potentially habitable worlds prove unsuitable for life, as we understand it, they might host forms of biology that operate according to principles we haven't yet discovered. The search for Earth 2.0 has become far more than a simple hunt for alternative homes for humanity. It has evolved into a comprehensive exploration of planetary science, stellar evolution, atmospheric chemistry, and the fundamental processes that create complexity in the universe. Whether or not we ever find convincing Earth twins, this search continues to expand human knowledge and deepen our appreciation for the remarkable planet we call home. In the quiet contemplation of these cosmic scales and the profound challenges they represent, we find perhaps the most important lesson that the search for Earth 2.0 has taught us. Earth itself, with its intricate web of interacting systems and the unlikely sequence of events that created and maintained its habitability over billions of years, appears to be far more unique and precious than we initially realized. The search for other worlds like our own has revealed just how extraordinary our own world truly is. The psychological impact of these discoveries extends far beyond the scientific community, touching on fundamental questions about humanity's place in the universe and our relationship with our home planet. The initial excitement about finding Earth 2.0 reflected deep-seated hopes about expanding human presence beyond Earth and reducing our species' existential risk by establishing footholds in other star systems. The gradual realization that these supposedly Earth-like worlds are likely uninhabitable forces us to confront uncomfortable truths about our cosmic isolation and dependence on the singular world that gave us birth. The cultural narrative surrounding Earth 2.0 discoveries reveals much about contemporary human anxieties regarding environmental degradation, resource depletion, and climate change on our home planet. The search for alternative worlds often carries implicit assumptions that finding habitable planets elsewhere might provide solutions to Earth's environmental challenges, either through eventual colonization or through the reassurance that habitable worlds are common enough that life will survive even if Earth becomes uninhabitable. This technological optimism, deeply embedded in Western scientific culture, assumes that human ingenuity can overcome any obstacle given sufficient time and resources. The discovery of potentially habitable exoplanets seem to validate this optimism by suggesting that alternative homes for humanity might exist throughout the galaxy, waiting to be reached through advances in propulsion technology and life support systems. However, the mounting evidence that most supposedly Earth-like exoplanets are actually hostile to life challenges this optimistic narrative in fundamental ways. Rather than providing potential escape routes from Earth's environmental challenges, the study of exoplanets reveals that habitable worlds may be so rare and distant that they offer no practical alternatives to maintaining habitability on our own planet. The distances involved in reaching even the nearest potentially habitable exoplanets are so vast that they effectively remove these worlds from any realistic consideration as destinations for human expansion. Proxima Centauri b, the closest potentially habitable planet at 4.2 light-years away, would require travel times of tens of thousands of years, using any propulsion technology we can currently envision developing. The technological and social challenges of maintaining human civilization during such extended journeys may be fundamentally insurmountable. Even more exotic propulsion concepts, such as those based on nuclear fusion, antimatter, or theoretical physics phenomena like Alcubierre drives, face energy requirements and engineering challenges that may prove impossible to overcome. The energies required to accelerate even small payloads to significant fractions of light speed are comparable to the total energy output of entire civilizations, making interstellar travel prohibitively expensive, even if the technical challenges could be solved. These practical limitations mean that the discovery of potentially habitable exoplanets, regardless of how Earth-like they might prove to be, offers no realistic solutions to environmental challenges on Earth. The search for Earth 2.0, rather than providing humanity with alternative destinations, has reinforced the critical importance of maintaining habitability on the one world we can actually inhabit. This realization carries profound implications for environmental policy and resource management on Earth. If habitable worlds are genuinely rare and unreachable, then Earth's biosphere represents not just our current home, but our only conceivable long-term habitat. The irreplaceable nature of Earth's environmental systems takes on new urgency when viewed from the perspective of galactic habitability research. The search for Earth 2.0 has also revealed unexpected dimensions of complexity in planetary science that have implications extending far beyond habitability research. The diversity of exoplanets we've discovered has challenged fundamental assumptions about how planetary systems form and evolve, forcing revisions to theoretical models that had been developed based solely on our understanding of the solar system. The prevalence of super-Earths and mini-Neptunes in exoplanet surveys, for example, has revealed that our solar system's architecture is actually quite unusual compared to most planetary systems. The absence of planets intermediate in size between Earth and Neptune, which are extremely common around other stars, suggests that planetary formation processes can follow pathways that have no parallel in our local experience. These discoveries have implications for understanding the formation and evolution of our own solar system that extend well beyond questions of habitability. The specific sequence of events that created the solar system's current configuration, with small rocky planets close to the Sun and large gas giants in the outer regions, appears to have been far from inevitable based on what we now know about planetary system diversity. The gravitational dynamics that shaped our solar system's architecture also played crucial roles in creating conditions suitable for life on Earth. Jupiter's presence in the outer solar system not only helped protect the inner planets from excessive cometary bombardment, but also influenced the delivery of water and organic compounds to Earth during the early phases of planetary formation. The specific timing of Jupiter's formation and migration history may have been critical for creating the conditions that allowed Earth to develop and maintain habitability over billions of years. Alternative scenarios for Jupiter's formation or orbital evolution could have led to very different outcomes for the inner solar system, potentially preventing Earth from becoming habitable or destroying habitability after it was established. These insights into solar system formation highlight another dimension of Earth's apparent uniqueness that goes beyond simple questions of planetary size and orbital distance. The specific sequence of events during our solar system's formation created not just one potentially habitable world, but a stable, dynamical environment that has maintained habitability over the extended periods necessary for complex evolution. The role of seemingly minor factors in determining long-term habitability becomes apparent when we consider the influence of our unusually large moon on Earth's evolution. The moon, likely formed through a massive collision between the early Earth and a Mars-sized object, plays multiple crucial roles in maintaining Earth's habitability that extend far beyond its obvious effects on ocean tides. The moon's gravitational influence stabilizes Earth's axial tilt, preventing the chaotic variations in obliquity that would occur if our planet lacked such a large satellite. Without this stabilization, Earth would experience extreme climate variations as its axial tilt wandered randomly over geological time, making it difficult for complex ecosystems to establish stable relationships with predictable seasonal cycles. The moon's tidal effects also influence Earth's rotation rate, gradually slowing our planet's spin over geological time while transferring angular momentum from Earth's rotation to the moon's orbital motion. This process has helped maintain Earth's rotation rate within ranges compatible with strong magnetic field generation and atmospheric circulation patterns that support stable climate. More subtly, the moon's gravitational effects on Earth's shape and internal structure may influence geological processes, including plate tectonics and volcanic activity. The periodic stresses induced by the moon's gravitational pull might contribute to maintaining the geological activity that drives chemical cycling between Earth's surface and interior, processes that are essential for long-term climate stability. The probability that other potentially habitable exoplanets possess similarly large moons remains essentially unknown, partly because such moons would be extremely difficult to detect using current observational methods, but also because the specific conditions that led to the moon's formation may be quite rare. The massive collision that created the moon occurred at just the right time in Earth's development, and involved objects of just the right sizes and velocities to produce a stable moon system rather than destroying the planet or ejecting all the material into space. These considerations add yet another layer to the growing list of factors that had to align properly to create Earth's habitability, making our planet seem increasingly unique rather than typical of habitable worlds throughout the galaxy. Each new factor we recognize as important for habitability makes the overall probability of finding truly Earth-like conditions more remote. The biological evolution component of Earth's habitability represents perhaps the most complex and least predictable aspect of what makes our planet suitable for complex life. The specific evolutionary pathways that led to oxygen-producing photosynthesis, complex multicellular organisms, and eventually intelligent life involved countless contingent events that could have unfolded very differently under slightly altered circumstances. The Great Oxidation Event, which fundamentally transformed Earth's atmospheric composition around 2.4 billion years ago, resulted from the evolution of cyanobacteria capable of splitting water molecules to extract electrons for photosynthesis. This biochemical innovation was not inevitable, and it required specific environmental conditions and evolutionary pressures that might not be replicated on other worlds. The oxygen production from photosynthesis initially caused a massive extinction event, since oxygen was toxic to most of the anaerobic organisms that dominated early Earth. The fact that life survived this crisis and eventually evolved to utilize oxygen for more efficient metabolism represents another contingent event that might not occur on other potentially habitable worlds. The evolution of complex multicellular organisms required additional innovations, including sexual reproduction, cell differentiation, and sophisticated intercellular communication systems. Each of these developments depended on specific evolutionary pressures and environmental conditions that might not exist on worlds with different geological, atmospheric, or stellar characteristics. Even the evolution of intelligence and technology, which many discussions of extraterrestrial life assume to be inevitable outcomes of biological evolution, may actually be quite rare events that depend on highly specific evolutionary pressures and environmental conditions. The particular combination of factors that led to human intelligence, including social organization, tool use, language development, and abstract reasoning capabilities, might be far more unusual than optimistic estimates of extraterrestrial intelligence typically assume. These evolutionary considerations suggest that even if potentially habitable exoplanets could maintain stable surface conditions suitable for life, the probability that they would develop complex ecosystems or intelligent civilizations might be vanishingly small. The search for Earth 2.0 might be looking not just for worlds with suitable physical conditions, but for worlds where the entire history of biological evolution unfolds in ways that parallel Earth's development. The temporal scales involved in biological evolution add another dimension of complexity that often gets overlooked in discussions of exoplanet habitability. Earth's biosphere required approximately 3.8 billion years to evolve from simple single-celled organisms to complex multicellular life forms, and another 500 million years to develop technological civilization. These evolutionary timescales are comparable to the lifetimes of the stars around which potentially habitable planets orbit, meaning that biological evolution on exoplanets would be racing against stellar evolution processes that gradually change the energy output and radiation environment that life depends upon. Many potentially habitable worlds might not have sufficient time for complex evolution to occur before their stars evolve beyond configurations compatible with surface habitability. Red dwarf stars, which host many of the potentially habitable exoplanets we've discovered, present particularly challenging evolutionary timescales. While these stars remain stable for much longer than sun-like stars, they also remain violently active for much longer periods, potentially preventing the emergence of life until most of their lifetimes have already passed. The narrow habitable zones around red dwarfs mean that planets must orbit very close to these stars to receive sufficient energy for liquid water, but this proximity makes them vulnerable to the intense radiation and stellar winds that characterize young red dwarfs. By the time these stars settle into stable configurations, suitable for habitability, they may have only a few billion years of stable lifetime remaining, barely enough time for complex evolution to occur even under ideal conditions. The question of whether life could emerge and evolve to complexity within such constrained timeframes remains largely unanswered. Earth's evolutionary history suggests that developing complex multicellular life requires billions of years of stable environmental conditions, but we don't know whether this represents a fundamental requirement or simply the particular pathway that evolution followed on our world. Alternative evolutionary scenarios might be possible under different environmental conditions, potentially leading to complex life forms through shorter developmental pathways. However, the specific environmental conditions that might enable accelerated evolution remain largely speculative, and there's no guarantee that such conditions would exist on potentially habitable exoplanets around red dwarf stars. The communication and detection challenges associated with potential extraterrestrial life add yet another layer of complexity to the search for inhabited worlds beyond Earth. Even if life commonly evolves on potentially habitable exoplanets, and even if some of that life develops technology and intelligence, the probability of detecting such civilizations remains extremely small due to the vast distances and short timescales involved in interstellar communication. The search for extraterrestrial intelligence has been ongoing for more than half a century without detecting any convincing evidence of technological civilizations elsewhere in the galaxy. This absence of detectable signals could indicate that technological civilizations are extremely rare, that they exist but don't use technologies we can detect, that they exist but avoid broadcasting signals that might reveal their presence, or that they exist but operate on timescales very different from human civilization. The potential habitability of exoplanets around red dwarf stars creates additional challenges for detecting technological civilizations, since any life forms that evolved on tidally locked worlds might develop very different technologies and communication strategies than those that evolved on rapidly rotating planets with day-night cycles similar to Earth's. The energy sources available to civilizations on tidally locked worlds might be fundamentally different from those that powered human technological development, potentially leading to technological pathways that would be difficult or impossible to detect using search strategies based on human technological experience. Even the concept of technological civilization might be irrelevant for life forms that evolved under environmental conditions radically different from those on Earth. The specific environmental pressures that drove human technological development, including seasonal variations, resource distribution patterns, and competitive interactions with other species, might not exist on other potentially habitable worlds. These considerations suggest that the search for technological signals from extraterrestrial civilizations might be systematically biased toward detecting life forms that evolved under conditions similar to those on Earth, potentially missing the vast majority of intelligent life in the galaxy if it developed under different environmental circumstances. The absence of detectable technological civilizations might not indicate that life is rare in the galaxy, but rather that the forms of life and intelligence that exist elsewhere operate according to principles that make them invisible to our current search strategies. The universe might be filled with forms of intelligence that we wouldn't recognize as such, because they don't conform to our expectations about what intelligence and technology should look like. This possibility transforms the apparent silence of the galaxy from evidence that we're alone to evidence that intelligence and technology can take forms so alien that we haven't learned to recognize them. The search for Earth 2.0, by revealing how different potentially habitable worlds are from Earth, suggests that any life forms that might exist elsewhere would likely be far more alien than science fiction has typically imagined. The economic and political dimensions of exoplanet research have also shaped public perceptions and expectations about the search for Earth 2.0 in ways that may have contributed to unrealistic optimism about finding habitable worlds. The substantial investments in space-based planet hunting missions create institutional pressures to produce results that justify continued funding, leading to press releases and media coverage that may emphasize the most optimistic interpretations of ambiguous data. the competitive nature of scientific research, particularly in high-profile fields like exoplanet science, can create incentives for researchers to announce discoveries in ways that maximize public attention and scientific impact, potentially contributing to a pattern of initial excitement followed by more sober reassessment as additional data becomes available. The media's role in translating complex scientific results into accessible public narratives also contributes to the cycle of optimism and disappointment that characterizes many exoplanet discoveries. The nuances and uncertainties that are essential parts of scientific research don't translate easily into the clear, definitive stories that make effective news coverage, leading to simplified presentations that may misrepresent the actual state of scientific knowledge. Public expectations about space exploration and the search for extraterrestrial life, shaped by decades of science fiction and popular media, may also contribute to unrealistic optimism about finding habitable worlds and eventually establishing human presence beyond Earth. These expectations create a cultural context in which discoveries of potentially habitable exoplanets are interpreted as steps toward eventual interstellar exploration, rather than as purely scientific endeavors, with no practical implications for human expansion. The disconnect between public expectations and scientific realities becomes particularly apparent when considering the technological and economic challenges involved in interstellar exploration, the energies required for interstellar travel, the timescales involved in reaching even nearby star systems, and the challenges of maintaining human civilization during extended space voyages are so extreme that they may be fundamentally insurmountable regardless of future technological developments. Even the most optimistic projections for future propulsion technologies suggest that interstellar travel would remain prohibitively expensive and risky for the foreseeable future, making the discovery of potentially habitable exoplanets irrelevant for practical purposes, even if such worlds prove to be genuinely Earth-like. The search for Earth 2.0 provides fascinating insights into planetary science and stellar evolution, but it offers no realistic alternatives to maintaining habitability on Earth itself. This reality forces a fundamental reassessment of humanity's long-term prospects and our relationship with our home planet. Rather than providing potential escape routes from Earth's environmental challenges, the search for habitable worlds reinforces the critical importance of environmental stewardship and sustainable resource management on the one world we can actually inhabit. The philosophical implications of these discoveries extend beyond environmental policy to encompass fundamental questions about the nature of life, intelligence, and our place in the cosmic order. The apparent rarity of truly habitable worlds suggests that life itself might be far more precious and unusual than optimistic estimates have typically assumed, transforming our perspective on the value and significance of terrestrial ecosystems. If Earth represents one of a very small number of worlds in the galaxy where complex life has emerged and thrived, then the preservation of our planet's biological diversity becomes not just an environmental imperative, but a cosmic responsibility. The species and ecosystems that exist on Earth might represent irreplaceable examples of biological complexity that could be lost forever if our planet's habitability is compromised. This cosmic perspective on Earth's biological heritage provides new arguments for conservation efforts and environmental protection that transcend traditional economic and political considerations. If life is genuinely rare in the galaxy, then allowing Earth's ecosystems to degrade through environmental mismanagement would represent a cosmic tragedy of unprecedented proportions. The search for Earth 2.0 has thus evolved from a hunt for alternative homes for humanity into a profound exploration of what makes our own world so remarkable and irreplaceable. Each potentially habitable exoplanet we study, regardless of its ultimate habitability prospects, deepens our appreciation for the extraordinary complexity and apparent rarity of the conditions that allowed life to emerge and flourish on Earth. The growing catalog of worlds that seem potentially habitable but prove to have fundamental problems provides a new lens through which to view Earth's history and development. The specific combination of factors that created and maintained habitability on our planet appears to be far more unusual and precious than we initially realized, transforming Earth from one example among many of habitable worlds to a singular achievement in the complex chemistry and physics of planetary evolution. In contemplating these vast scales and profound implications, we find ourselves returned to questions that have occupied human thought since we first looked up at the night sky and wondered about our place among the stars. The search for Earth 2.0 has provided some answers to these ancient questions, but perhaps more importantly, it has revealed new depths of complexity and mystery in the processes that create and sustain life in the universe. The universe revealed by modern exoplanet research is simultaneously more diverse and more lonely than previous generations imagined. It contains countless worlds of types that have no parallel in our solar system, operating according to physical and chemical principles that stretch our understanding of planetary science. Yet none of these worlds appears to offer the combination of characteristics that makes Earth suitable for complex life. This paradox, abundance without habitability, diversity without familiarity, challenges our assumptions about the nature of planets, stars, and life itself. The search for Earth 2.0 continues, driven by the fundamental human desire to understand our place in the cosmos, but it has already provided insights far more profound than simple planet hunting was expected to yield. In the quiet of evening contemplation, as you drift towards sleep while considering these cosmic questions, perhaps the most remarkable realization is how the search for other worlds, like our own, has revealed the true uniqueness of the world beneath our feet. Earth 2.0 may exist somewhere in the vast galaxy, but until we find it, we remain the custodians of the only known example of a world where matter has organized itself into the extraordinary complexity we call life. This responsibility, cosmic in scope and intimate in its daily implications, transforms every sunset, every forest, every ocean wave into a reminder of how precious and unlikely our cosmic home truly is. The search for Earth 2.0 continues, but it has already given us the most important gift it could provide: a deeper appreciation for Earth 1.0 and our role as its temporary caretakers in the long story of cosmic evolution. The future of exoplanet research promises to bring even more sophisticated observations and theoretical insights that will further refine our understanding of habitability throughout the galaxy. The next generation of ground-based telescopes, with their unprecedented light-gathering capabilities and advanced coronagraph systems, may finally provide detailed atmospheric analysis of nearby potentially habitable worlds. Yet even these remarkable advances will likely reveal new layers of complexity rather than simple answers about extraterrestrial habitability. The development of artificial intelligence and machine learning techniques specifically designed for exoplanet research represents another frontier that may revolutionize how we search for and characterize potentially habitable worlds. These computational approaches can identify subtle patterns in observational data that human analysts might miss, potentially revealing new categories of potentially habitable planets or new indicators of atmospheric and surface conditions. However, the application of artificial intelligence to exoplanet research also carries risks of amplifying the observational biases and theoretical assumptions that already influence our search strategies. Machine learning algorithms, trained on Earth-based examples of habitability, might systematically overlook forms of habitability that operate according to different principles, potentially missing the most abundant forms of life in the galaxy because they don't match the patterns these systems have learned to recognize. The generational implications of our growing understanding of cosmic habitability extend far beyond scientific research to influence how we think about the future of human civilization and our responsibilities to future generations. The children growing up today will inherit a world where the apparent rarity of habitable planets is taken for granted, fundamentally shaping their perspectives on environmental stewardship, technological development, and humanity's long-term prospects. This generational shift in cosmic perspective may prove to be one of the most significant cultural changes driven by exoplanet research. Previous generations could maintain optimism about human expansion beyond Earth based on the assumption that suitable worlds were relatively common and accessible. Today's children will grow up knowing that other potentially habitable worlds are likely rare, distant, and probably unsuitable for human habitation, regardless of future technological developments. This knowledge transforms questions of environmental policy and resource management from local concerns to cosmic imperatives. If Earth represents humanity's only realistic long-term home, then decisions about climate change, biodiversity loss, and environmental degradation take on existential significance that extends far beyond traditional economic or political considerations. The psychological adaptation to cosmic loneliness represents a profound challenge that human culture is only beginning to address. The realization that we may be alone in a galaxy filled with worlds that seem habitable but are actually hostile to life creates a form of existential isolation that has no parallel in previous human experience. We are potentially the only conscious observers in a local universe filled with wonders but devoid of other minds capable of appreciating them. This cosmic loneliness differs fundamentally from the social isolation that individuals might experience because it encompasses our entire species and all the life on our planet. There may be no other consciousness anywhere within thousands of light years capable of sharing our wonder at the universe, no other civilizations working to understand the same cosmic processes that fascinate us, no other worlds where matter has organized itself into the complex patterns we call life. Yet this isolation also creates a unique form of cosmic significance. If consciousness and complex life are genuinely rare in the universe, then the emergence of human awareness represents an extraordinary achievement in the long story of cosmic evolution. We become not just observers of the universe, but the universe's primary means of understanding itself, at least within our local region of space and time. The spiritual and existential dimensions of this realization extend beyond scientific materialism to touch on fundamental questions about meaning, purpose, and our relationship with the cosmos. If we are alone or nearly alone in the galaxy, then human consciousness becomes invested with a cosmic importance that transcends individual lives or even our species' survival. The art, literature, music, and philosophy created by human civilization become not just cultural achievements, but cosmic events, moments when the universe develops new forms of self-awareness and creative expression. Every scientific discovery, every work of art, every moment of genuine understanding represents a development in the universe's capacity for consciousness and meaning-making. This perspective transforms human culture from a local phenomenon relevant only to our species into a cosmic development of potentially universal significance. The thoughts, emotions, and creative works that emerge from human consciousness might be the only such phenomena occurring anywhere within vast regions of space, making our cultural development a matter of cosmic rather than merely local importance. The relationship between individual human lives and cosmic significance becomes particularly poignant when viewed from this perspective. Each person's unique experience of consciousness, creativity, and understanding contributes to the universe's total capacity for self-awareness. Individual deaths represent not just personal losses, but reductions in the cosmos's ability to know and understand itself. This cosmic significance of individual consciousness provides new perspectives on questions of meaning and purpose that have occupied human philosophy throughout our cultural development. Rather than being insignificant specks in a vast universe, we become central players in the cosmos's ongoing project of self-discovery and creative development. The environmental implications of cosmic loneliness extend beyond simple resource conservation to encompass the preservation of the universe's only known example of complex biological organization, Earth's ecosystems represent not just local ecological communities, but cosmic experiments in the organization of matter and energy into living systems. The extinction of species on Earth becomes, from this perspective, not just an environmental tragedy, but a cosmic loss, the disappearance of unique solutions to the challenges of biological existence that may never be replicated anywhere else in the galaxy. Every ecosystem, every species, every individual organism represents a unique configuration of matter and energy that contributes to the universe's total inventory of biological complexity. This cosmic perspective on biodiversity provides powerful new arguments for conservation efforts that transcend traditional economic or political justifications. The preservation of Earth's biological heritage becomes a cosmic responsibility, maintaining the universe's only known examples of how matter can organize itself into the remarkable patterns we call life. The temporal dimension of this responsibility adds urgency to conservation efforts when viewed against the timescales of cosmic evolution. Earth's biological complexity has taken billions of years to develop, but it could be destroyed within decades through environmental mismanagement or catastrophic events. The window of opportunity for preserving this cosmic achievement may be remarkably narrow compared to the vast timescales over which it developed. Future evolutionary possibilities on Earth also take on cosmic significance when viewed from this perspective. The continued evolution of life on our planet represents the universe's ongoing project of developing new forms of biological complexity and consciousness. Protecting the evolutionary potential of Earth's biosphere becomes not just an environmental goal, but a cosmic imperative. The coevolution of human technology and Earth's ecosystems represents a particularly critical phase in this cosmic evolutionary process. Our species' unique combination of consciousness, technological capability, and ecological impact gives us unprecedented influence over the future development of complexity on Earth and potentially beyond. The choices we make regarding artificial intelligence, genetic engineering, ecosystem management, and space exploration will determine whether Earth continues to serve as a center for the development of complexity and consciousness, or whether our planet's unique achievements in biological organization are diminished or destroyed through technological mismanagement. The search for Earth 2.0, by revealing the apparent rarity of worlds capable of supporting complex life, has transformed these technological and environmental choices from local concerns into cosmic responsibilities. We are not just managing resources and technologies for human benefit, but serving as stewards of the universe's most remarkable known achievements in the organization of matter and energy into conscious, creative systems. The long-term future of Earth's habitability adds another temporal dimension to these cosmic responsibilities. Even if we successfully preserve Earth's current biological complexity, our planet faces inevitable changes driven by stellar evolution that will eventually make it uninhabitable for complex life. The gradual brightening of the sun over geological time will eventually trigger a runaway greenhouse effect that boils away Earth's oceans, ending the story of terrestrial biology regardless of how well we manage environmental challenges in the near term. This inevitable future creates a poignant temporal framework for considering our cosmic significance. Earth's role as a center for biological complexity and consciousness is temporary on cosmic timescales, making our current epoch simultaneously more precious and more urgently important for the universe's ongoing development of self-awareness and creative expression. The possibility of extending Earth's biological heritage beyond our planet takes on new significance when viewed from this temporal perspective. While the distances and challenges involved in interstellar travel make human colonization of exoplanets unrealistic, the preservation of Earth's biological information through other means might be achievable even if the worlds capable of supporting that life remain beyond our reach. Digital preservation of biological and cultural information, advanced forms of artificial intelligence capable of maintaining and developing human knowledge and creativity, and other technological approaches to preserving Earth's achievements might offer ways to extend our planet's cosmic significance beyond the limited time frame of terrestrial habitability. Yet these technological solutions to cosmic impermanence raise profound questions about the nature of consciousness, creativity, and biological existence that we are only beginning to explore. The preservation of information is not the same as the preservation of the conscious experience that gives that information meaning, and the complex relationships between matter, energy, and awareness that characterize life may not be reproducible through technological means alone. The search for Earth 2.0 has thus evolved from a relatively straightforward astronomical project into a comprehensive exploration of what makes existence meaningful and significant on cosmic scales. The apparent absence of other readily habitable worlds forces us to confront fundamental questions about consciousness, creativity, biological complexity, and our responsibilities as the universe's known centers of self-awareness and creative expression. The continuing search itself becomes an expression of these cosmic responsibilities, representing humanity's commitment to understanding our place in the universe and exploring the possibilities for consciousness and complexity beyond our local experience. Even if we never find convincing examples of Earth-like worlds, the search process continues to expand human knowledge and deepen our appreciation for the remarkable achievements that Earth's biological evolution represents. The technological developments driven by exoplanet research also contribute to humanity's broader project of understanding and interacting with the cosmos in increasingly sophisticated ways. The precision required for detecting and characterizing distant planets pushes the boundaries of observational astronomy, materials science, and computational analysis in ways that have applications far beyond planet hunting. These technological advances represent another dimension of humanity's cosmic significance, demonstrating our species' unique capacity for developing tools and techniques that extend our awareness far beyond the limitations of individual human perception. The telescopes, spacecraft, and analytical methods developed for exoplanet research become extensions of human consciousness that allow us to explore and understand regions of space and time that would otherwise remain forever beyond our reach. The collaborative nature of modern exoplanet research also reflects humanity's capacity for organizing collective efforts that transcend individual, national, and cultural boundaries in pursuit of cosmic understanding. The international cooperation required for large-scale astronomical projects demonstrates our species' potential for working together on challenges that extend far beyond immediate practical concerns. This capacity for collaboration on cosmic scales provides hope that humanity might successfully address the environmental and technological challenges that our cosmic responsibilities entail. The same qualities that enable effective international cooperation in astronomical research might also support the long-term environmental stewardship and technological development that preserving Earth's biological heritage will require. The educational dimensions of exoplanet research contribute to developing the scientific literacy and cosmic perspective that future generations will need to fulfill their roles as stewards of the universe's known centers of complexity and consciousness. Every student who learns about exoplanets, stellar evolution, and the challenges of habitability develops a deeper appreciation for Earth's uniqueness and humanity's cosmic responsibilities. The cultural impact of exoplanet discoveries extends beyond formal education to influence art, literature, philosophy, and popular culture in ways that gradually reshape human perspectives on our place in the universe. The growing awareness of cosmic loneliness and Earth's apparent uniqueness is slowly becoming integrated into human cultural consciousness, influencing how we think about meaning, purpose, and our relationships with each other and our environment. As you settle into the quiet moments before sleep, contemplating these vast scales of time and space, perhaps the most profound realization is how the search for Earth 2.0 has transformed our understanding of home. We began looking for other worlds like our own, hoping to find evidence that habitable planets were common and that humanity might someday expand beyond Earth to establish civilization among the stars. Instead, we discovered that Earth itself is far more remarkable and unique than we ever imagined. The combination of factors that created and maintained habitability on our planet appears to be extraordinarily rare, making Earth not just our current home, but potentially the universe's most significant achievement in the organization of matter into living systems. This discovery transforms every moment of conscious experience into a cosmic event, every breath into a participation in the universe's only known experiment in complex life, every thought into a contribution to the cosmos's capacity for self-understanding. We are not just inhabitants of Earth, but partners in the universe's ongoing project of developing consciousness, creativity, and meaning. The search for Earth 2.0 continues, carried forward by our deep human need to understand our place among the stars and explore the possibilities for life beyond our cosmic home. Whether we ever find convincing Earth twins or confirm that we are alone in our local region of the galaxy, the search itself represents one of humanity's highest achievements in curiosity, creativity, and cosmic responsibility. In the gentle transition towards sleep, surrounded by the quiet wonder of a universe that may know consciousness only through our brief but brilliant presence within it, we find ourselves both humbled by the vastness of space and time and elevated by our unique role as the cosmos's way of knowing and understanding itself. Earth 2.0 may exist somewhere in the depths of space, but until we find it, we remain the caretakers of Earth 1.0, the universe's most precious and irreplaceable achievement in the long story of cosmic evolution.